Hello, good morning, everybody. Welcome to International Conference on Advance in Functional Materials 2021, UCLA. So today we are in the second day of the conference, and we are still waiting for our session chair, Dr. Ilham. Are you here? Can you listen me, please?
Yes, hello.
Still we have 1 minute, and we are waiting for our session chair, Dr. Ilham Sahrai. Okay, he's here. She's here. Okay. Welcome, Dr. Ilham. Now you are the session chair for this session.
Good morning, everyone. Thank you for joining us for the session on functional materials for energy storage and conversion. So we start the first presentation, engineering of low cost and environmentally benign catalysts for thermal assisted photocatalytic hydrogen production. The presentation is given by Sergey Nikitenko.
Yes, thank you.
Sergey, please start the presentation.
Yeah, thank you. So, can you see my presentation?
Yes, we can see your presentation.
Okay, let's go. Yes, yeah, okay, it works now. So hello everyone, I am Sergey Nikitenko and I'm working at the Institute of the Separation Chemistry in Marcoule Research Center, and this institute is situated in the south of France. And today I'll talk about the photothermal production of hydrogen. So we know that production of hydrogen from renewable sources is a key point of the green energetics now. And today there is only one technology for production of green hydrogen, is an electrolysis of water. However, this hydrogen is quite expensive, and today only about 4% of hydrogen is produced by this technology. There are several emerging technologies, and among them there is a photocatalysis under solar light and photoelectric catalysis. However, the performance of both technologies depend on catalyst, and such catalyst should meet some very strict requirements. They should be active under solar light, they should be stable, they should not be very expensive, so it means that we should avoid use of noble metals, and they should not be toxic. In addition, there is a problem of the efficiency of the photocatalytic processes. And now we know that introducing heat into photocatalysis can significantly improve the photoconversion efficiency. And the photothermal catalysis attracts a lot of attention last decade. Here I presented the diagram about with the number of publications which grows very rapidly last decade. And also you can see here the references on some very recent reviews dedicated to photothermal catalysis. However, what the photothermal catalysis means, in fact, this is a very complex phenomenon. And the photothermal processes, we can divide it on three big groups. First is photodrive and thermocatalysis. It means that the light is used just to heat the catalyst, and then catalyst works by thermal activation. Another group is photothermal co-catalysis. It means that both light and heat contributes to activations of the catalytic processes. And the third group, and this photothermal co-catalysis very often is observed for the catalyst with noble metals like platinum, gold, so another noble metals. And the third group is a thermal assisted catalysis. It means that we have a photonic activation of the catalyst, but heat can contribute to enhance the yield of the photocatalytic processes. And today I'll focus on this kind of photothermal effects. So we studied titanium oxide, core shell nanoparticles as a catalyst. This catalyst we have prepared using commercially available titanium metal nanoparticles and by sono-hydrothermal treatment. What it means, sono-hydrothermal treatment? It means simultaneous action of hydrothermal conditions and ultrasound. Here on the right, you can see the sono-hydrothermal reactor developed in our laboratory. And you see that ultrasonic horn is directly inserted into hydrothermal reactor. What is the effect of ultrasound in this case? Due to the acoustic cavitation, first we can disperse very effectively the powders inside the hydrothermal reactor, and also we can accelerate the hydrothermal processes. And titanium oxide nanoparticles have been prepared by sono-hydrothermal treatment in pure water. So here you can see the high resolution TM images of titanium-0 nanoparticles. They are quasi-spherical, and the size is about 90 nanometers. In the middle, you can see ultra microtomographic images of single titanium-0 nanoparticles. And clearly, you can see some shell at the surface. This is a passivating oxygen-enriched shell. I'll talk later about its composition. After sono-hydrothermal treatment, the particles preserve their spherical or quasi-spherical symmetry, but at the surface we can clearly see appearance of the nanocrystals with a size around 10-15 nanometers, and analysis shows this is anatase titanium oxide. So at this slide, you can see the XRD and XPS analysis of our particles. For titanium-0, so titanium-0 nanoparticles are composed mostly from alpha metallic titanium, but also we observed some presence of titanium suboxide, titanium-3O. This is very rare phase of titanium. It's quite interesting. And the spectrum of titanium-0 nanoparticles you can see on the right. And we see the presence of titanium-0, but also we can see the presence of other oxidation state of titanium lower than 4, and it can be attributed to suboxides of titanium, but also the presence of titanium-4. And titanium-4 we don't see by XRD. It means that this form presents at the surface as some amorphous phases. When we start to heat, we see that progressively with the temperature of sono-hydrothermal treatment, the concentration of titanium suboxide decreases. And after 160 degrees, we don't see any titanium suboxide. And also we see oxidation of titanium-0 and increase of the concentration of titanium anatase phase. From this data, we can suggest the following mechanism of titanium oxide shell formation. So if the temperature is lower than 160 degrees, in this case, anatase formed by oxidation of titanium suboxide or by crystallization of amorphous titanium-4. At higher temperature, we also titanium zero and titanium nanoparticles, they are black. So they absorb light in very wide range. And the spectrum of titanium zero nanoparticles show very broad continuum from UV to near infrared line. And it's due to the interband transitions of titanium metal. But we don't see any plasmon bands. It means that titanium zero is not plasmonic material. For titanium oxide, we also see this interband transitions of titanium zero, but also the band gap at 350 nanometers, which is typical for titanium NTS. So we have some combination of optical properties of titanium metal and titanium oxide. And on the right, you can see the photoluminescence spectra for crystalline the titanium oxide NTS. We can see emission band around 360 nanometers, which is quite characteristic for recombination of electron and holes. However, for titanium oxide partial nanoparticles, we do not see this band, which indicates that we have quite efficient electron hole separation with partial nanoparticles. And now I'll present some results about catalytic hydrogen production. So we use glycerol aqueous solution, glycerol as a sacrificial reagent. And you can see our photocatalytic reactor. It's a glass-made reactor with temperature control. And we use argon flow. So we bubble just argon through this reactor. As a light source is a xenon lamp, which provides mostly visible and near-infrared light, but some UV also. And the analysis is performed in the outlet gas using mass spectrometer. At this slide, I want to show some results about hydrogen, about photocatalytic hydrogen production. On the left, you can see the hydrogen emission plots for different kind of particles. The blue one is a titanium with a very low content of titanium oxide at the surface. And you see that the yield of hydrogen is extremely low, whatever the temperature. If the concentration of titanium at the surface increases, the yield of hydrogen also increases. It means that the presence of titanium oxide as a shell is required for photocatalytic activity of this kind of material. And another interesting point is that when we increase the temperature, you can see that progressively we see increase of hydrogen production. And then at high temperature, when the lamp is off, so we have no light, there is no hydrogen even at quite high temperature. So in this case, we really have photonic origin of the process. And these curves allows us to calculate the activation energy of the process. And depending on this value varies from 25 to 31 kilojoule per mole. This is much less than the activation energy of chemical bonds. So the temperature does not play a role of activator of chemical bonds in this process. Another interesting observation that we do not observe emission of carbon dioxide or carbon monoxide or methane during the photocatalytic process. In the outlet gas, we see only hydrogen. However, at the same time, the solution acidifies during sonolysis. So pH decreases, as you can see here, from 6 to approximately 4 hours of photolysis. And so we can conclude that in our conditions, glycerol is oxidized to some organic acids without emission of carbon dioxide. Another interesting thing is that if the temperature is quite high, we can see hydrogen emission even without any glycerol, just in pure water. if you compare the yield of impure water and glycerol, with glycerol it's higher, of course. But this is quite interesting that even in pure water at high temperature, we can observe the hydrogen. So finally, we can suggest some mechanism explaining photothermal effect in our system. First of all, light is absorbed by both, by titanium core and by titanium oxide shell. Titanium core absorb all kinds of lights, UV, near-infrared, and visible light. Titanium oxide can absorb some part of UV. So when titanium metal absorbs the light, due to the non-radiative Landau damping mechanism, electron hole pairs can be formed. But the lifetime in metals of such kind of pair is extremely short. So due to the rapid charge separation, we can stabilize such kind of electron holes. So electrons are accumulated in metal and holes in titanium oxide shell. And also by quite usual mechanism, electron hole pairs can be formed in titanium oxide shell. In this view, the photothermal effect.
Thank you very much. Unfortunately, we are at the end of our 15 minutes, so if you can wrap up.
Okay, I'm finished. It's okay. It's just you can see our suggestions about mechanism, and at the end, I will just thank my colleagues from the institute and from the University of Montpellier and CNRS for support. And thank you for your attention.
Thank you very much to you and the whole team from University of Montpellier. If anyone has questions, I suggest that you reach Sergey. His email is in the program. We are now getting ready for our second presentation.
Okay, so thank you. I will be happy to answer.
Yeah, thank you. So we are now getting ready to our second presentation for this session. The second presenter is Mayo Fang Chi. Mayo Fang is from Oak Ridge National Lab, and she will be talking.
Sorry, can the first speaker stop sharing, or because I can't share my screen right now?
Oh, Sergey, you need to stop sharing. Thank you. So our second presentation is Beyond Structural and Chemical Imaging in a TEM, New Opportunities for Understanding Interfaces in Energy Materials. Maya Fang, can you start sharing your presentation?
Can you see it?
Yes, perfect. Thank you. You can start.
Thank you, and thank you for, actually, I would like to thank the organizers for the opportunity first. And I haven't visited UCLA, but I guess it's a virtual visiting right now. So today I'm going to talk about probing interfacial stability in all solid state batteries using scanning transmission electron microscopy. So what really inspired my interest actually a couple of years ago in all solid state batteries is this Toyota's roadmap published in 2014. This roadmap is still actually mostly valid. It tells us that while the lithium-ion batteries that are based on flammable liquid electrolytes is hitting its theoretical limitation in energy density, all solid-state batteries offer a much higher energy density, and it is an essential future battery configurations. In addition to higher energy density, I just mentioned that there are more benefits of solid-state batteries, such as it's safer and charge faster, more compact, last longer. So it's a great perspective as the future energy storage technology can also be clearly seen by these overwhelming headlines you perhaps have seen recently. And however, why it takes decades to have a commercial project. So this is because we have had and still have technical challenges. In my opinion, issues related to interfaces have been the major challenge, and some of them actually still remain. In a solid state batteries with a polycrystalline solid electride, the interfaces include those between electride and electrode, as well as the grain boundaries within solid electride. Interfacial challenges often result in unknown larger interfacial resistivity, unexpected dendrite growth, or limited cyclability. So since the interfaces are embedded and spatially confined, they are very difficult for most characterization techniques. But looking at local features is the strength of scanning transmission electron microscopy. So we call it STEM. For those of you who are not very familiar to STEM, the way how STEM works is by resting a tiny electron probe on a specimen. We integrate the electrons after they interact with the specimen, utilizing the annular shaped detectors. Then you can get the atomic resolution images, and then you can also put your electron probe at the specific atomic column you're interested in and find out the chemical species as well as chemical bonding information. So very recently, monochromated EOS actually allow us to not only being able to look at the chemistry and the bonding, but also the optical responses, such as band structure, plasma excitations, and as well as the vibration responses in a microscope. First, I would like to introduce you our recent study of looking at a LiPo lithium metal interface using in situ STEM. While a stable interface in a battery requires an energy overlap between the condension band maximum of solid electride with the lithium redox potential, the reality is that there is often a gap. And for example, it is so here is a theoretical calculation by a Maryland group, and it shows that there is a potential gap between the LiPo and the lithium redox potential, which is around 0.69. And for the LLZO is actually 0.05 around volts. So this means that most of those solid electride actually react with lithium metal when they are adjacent to each other in a cell. So however, for example, LiPo here, today I will give you mainly the example is the LiPo, how we use the microscopy to look at the LiPo lithium metal interface. But for LiPo, this specific case, electrochemical measurements show that the LiPo has an exceptionally long cycle life. So here is a work we published a couple of years ago. As you can see here, the capacity actually can retain around 90% even after 10,000 times cycles. So this actually contradicts with the theoretical calculation that the interface actually is supposed to react when it contacts with the lithium metal. So this drove our the electron microscopy study. So here what we use a scanning tunneling microscopy tip-based bias encoder, and this holder allow us to put the specimen and the lithium metal coated tungsten tip in a microscope and then make contact. So putting them together and then in situ in the microscope and watch what happens. And we can also apply a bias, just simulating the electrochemical cycling on a battery. So on the right side is actually a video. So on the as you can see here, this one on the left bottom is the lithium metal, while on the top right is the LiPo. So I would like you to pay attention to the surface of the LiPo and how it works when we make the contact of these two materials. As you can see here, there is a very obvious surface swallow on the LiPo side, which indicating the chemical reaction and happening at this interface, while it actually stopped when around like the interface layer is around 16 nanometer, and then it kept stable over time, and even after we applied a 5 volts voltage between these two materials. So we did a more detailed EOS electron energy loss spectroscopy, and we found out that there is a decomposition reaction occurred, and which corresponding to this reaction. So which means that LiPoN decompose to these 3 compounds. So among these three compounds, the lithium phosphor actually has a concerning electronic conductivity, which means that it is not stable with lithium metal and may further react when it is contacted with lithium metal. So this still can't actually explain the excellent in interfacial cyclability we see in the electrochemical measurement. And however, the elemental mapping reveals the secret behind that. As you can see here I would like you to pay specific attention to the phosphor map and the map, and the oxygen and the overlay of this map. As you can see here, actually the phosphor signal is separated so here at the outermost surface is oxygen rich, while phosphor is separated from the lithium metal with a lithium oxide layer, while lithium oxide is stable with the lithium metal. So this actually explains that why the reaction doesn't propagate continuously, and why this interface tends to be stable under the electrochemical cycling. So I would like to talk about the second example, which is on reviewing dendrite growth mechanism in solid electrolytes. Dendrite growth is actually a trouble, but I mean the most critical or most challenging phenomenon in many current lithium-ion batteries, and as well as the solid-state batteries. So in polycrystalline ceramics, such as LLZO is the lithium lanthanum zirconium oxide. This is a garnet structural material, and it often has seen that the dendrite grow preferentially along the grain boundaries. So many previous studies reviewed that surface defects and the porosity on the surface of LLZO play an important role. But it is very difficult to explain why they preferentially grow along the grain boundaries. So what we have done, actually looking at those grain boundaries, is to combine the cryo-electron microscopy, monochromated EOS, and the in situ TEM, and to trying to figure out what it is going on at the grain boundary, why the grain boundary is preferentially for those dendrites to grow. So this work, we use the hot-pressed LLZO pellets synthesized by Jeff Sakamoto's group at the University of Michigan. And the pellets are highly dense. Actually, they are like higher than 97%, and the porosity in that case is not a concern. And we did also EBSD analysis, shows that the grains are completely randomly oriented. So it's not really like the small angle grain boundary. So and then we did a high resolution images of those grain boundaries, of many grain boundaries in LLZO. We found out that they are composed of high index interfaces, indicating that the atomic scale structure of grain boundary actually deviate from that of the bulk. And more EDX and EOS analysis showing that actually actually like there is a very slight drop in oxygen content, while the concentration of all cations, even including the alumina, which is a dopant in this material, are nearly the same in the grain boundary and as well as in the grain bulk. So what is going on with actually those grain boundary? So low loss yields, which I just mentioned earlier, we also use called like monochromated yields, actually reveals the obvious difference at some grain boundaries compared to that of the bulk. So here the grain boundary spectrum is highlighted as red, and it's difficult to see the difference between this spectrum versus the bulk one. But if you overlay them, you can see the difference very clearly. So here on the top right, and the red spectrum corresponding to the one from grain, and the blue one is from the grain boundary. And you can see here on the spectrum on the grain, actually you can see the 5.7 EV very easily as a band gap very easily, while the grain boundary wise here the electron all the way extended to like around 2 EV. So which means that the grain boundary band gap is much narrower than the grain. So here this is showing you like for each of those spectrum we did the analysis, and you can see it very clearly. So such a band gap. Sorry.
We are at 11:40. If you can wrap up, please, that would be great.
Okay, yeah, I guess I also started a little late, but so such a band gap reduction is not uniform among all grain boundaries, and the different local, actually grain boundary shows a very different band gap. And we did also the in situ biasing TEM, and which proves that it is the lithium metal preferentially infiltrated along the grain boundaries compared to the bulk, and the more fiber sectioning imaging reveals the presence of isolated grain dendrites within the shorted LLZO, and things that due to the time limitation, so I won't explain in detail. But the conclusion is that there's actually, in addition to the dendrite growth from an interface, which we are familiar to for the lithium ion batteries, and there is another mechanism we found is that the scattered lithium nucleation could happen within the grain boundary, and then they connect and form the grain boundary dendrite network leading to short circuit. And I won't talk about this. And at the end, I would like to thank my collaborators. So all work I talked about today are not possible without the contribution of each single person listed here. And with this, I would like to thank you for your attention. And if you have any questions, feel free to email me, since we have the time limitation here.
Thank you very much, my Frank. And yes, I invite everyone, if you have questions, to email her. Unfortunately, we have to move to our next presentation. Our next presenter is Kei Noda from Keio University, Japan. And his presentation is anodized metal oxide nanotubular arrays for gas phase photocatalysis and photo-induced high purity hydrogen production. So, Kei, I invite you to start your presentation.
Okay. Yeah. Thank you for your kind introduction. Can you see my screen?
Yes.
Okay, thank you. So now I'll start. Good morning. I'm Kei Noda from Keio University, Japan. So now I'll talk about our recent results on anodized metal oxide nanotubular arrays for photocatalysis. Electrochemical anodization is one of the surface finishing techniques for various transition metals. Anodization technique will lead to the formation of metal oxide layers on the metal surfaces, as shown in this slide. In particular, fen electrolytes, including both fluoride and polyols for anodic metal oxide is used. Self-aligned tubular arrays can be prepared as shown in this slide. Actually, well-aligned metal oxide nanotubes of wide bandgap oxide semiconductors, such as titanium dioxide and hematite with smooth walls, can be formed. These self-aligned nanotubular structures with large specific surface areas are intensely examined toward photocatalytic and photoelectrochemical applications. Now, at first, promising candidate as a visible light responsive photocatalyst with an indirect band gap of 2.2 electron volt. The potential application of hematite will be economically viable, since iron is one of the most abundant metals on the Earth. However, hematite has rapid electron-hole pair recombination and poor electrical conductivity. To overcome these disadvantages, various researches on material synthesis, doping, theoretical calculations have been widely conducted. With this background, self-aligned hematite nanotubes have been expected toward high-performance photocatalytic application. So this slide shows how we prepared hematite nanotubular arrays. Hematite nanotubular arrays were fabricated by two-step anodization method. After the first anodization process, the anodized iron sheet was sonicated in organic solvents to clean the sample surface. Then we performed second anodization process, and the uniformly anodized iron oxide with red-brown color was obtained. After that, the anodized samples were annealed in oxygen atmosphere for crystallization in hematite phase. Now you can see the scanning electron microscope images of the samples. These images show vertically aligned nanotubular structures with an average pore size of 20 nanometer and length exceeding 2 micrometer. For aiming at solar hydrogen production, the energy band structure of photocatalytic material should be considered. Hematite itself is not capable of generating hydrogen because its energy level of the conduction band edge is more positive than the hydrogen reduction potential. Therefore, loading of catalysts that promote proton reduction is essential toward solar hydrogen production based on hematite nanotubular arrays. Here, we have focused on p-type Q+ oxide, Cu2O, as one of the co-catalysts for hematite, because Q+ oxide possesses a band gap of 2.1 electron volt, and its conduction band edge is located more negative related to the hydrogen reduction potential. Moreover, the employment of noble metal-free co-catalysts such as Cu2O is desirable in terms of cost effectiveness and sustainability. In this work, we utilized pulse electron deposition method for Cu2O nanoparticle growth. Pulse electron deposition has advantages in uniform and dense deposition of small nanoparticles. Then, photocatalytic hydrogen production with a composite of hematite nanotubular arrays and Q+ oxide nanoparticles was examined in a homemade measurement setup as shown in this slide. The hydrogen amount from decomposition of gaseous mixture of water and methanol with a mixing ratio of 1:1 in volume was evaluated by using a gas chromatograph. The measurement cell was connected to the gas chromatograph by a gas sampler. Prior to visible light radiation, the gas lines were patched with nitrogen gas several times, and generated gases over the sample under the light radiation was stored and circulated continuously, like this. Then the condition of light radiation was written in this slide. So this slide presents the date plot of the hydrogen amount and the light irradiation time for the composite sample of hematite and Q+ oxide, only hematite, only Q+ oxide, and platinum-loaded hematite samples. The hematite Q+ oxide composite revealed hydrogen production under visible light radiation. However, hydrogen production could not be detected with other 3 samples. This result indicates that Q+ oxide nanoparticles deposited on hematite nanotubes plays an important role in reducing protons to hydrogen, owing to its conduction band level more negative than the hydrogen reduction potential. Thus, the Q+ oxide nanoparticles can work as noble metal-free co-catalysts for gas-based photocatalysis based on visible light responsive N-type semiconductors. Now I'll move on to the second topic on high-purity hydrogen production. Considering the hydrogen gas supply for practical uses, all the hydrogen reforming units must be followed by hydrogen purification units for separating generated hydrogen from other byproduct gases, such as carbon dioxide and oxygen. This issue can limit the miniaturization of hydrogen production systems and the further development of on-site reformers toward mobile application of hydrogen energy. For solving issues on hydrogen usage mentioned in the previous slides, we proposed a photoactive hydrogen production separation membrane reactor, which consists of an array of nanotubular photocatalysts and a hydrogen permeable metal, as shown in this slide. The whole thickness of the membrane reactor was only several micrometers. Here, anodized titanium dioxide nanotubular array was employed as a photocatalyst for electrolysis-plated palladium thin film as a hydrogen purification part. Liquid or vapor fuels, such as alcohols or water, can be reformed by photocatalysis on TiO2. The hollow parts of titanium nanotubular arrays serve as a path for generated hydrogen to the inner surface of a palladium layer, and then high-purity hydrogen gas was obtained quickly from the backside of the palladium layer. So this slide shows how we prepare a barrier membrane of TiO2 nanotubular array and palladium layers. The anodized titanium sheet was coated with a palladium film by electrolysis plating. At first, palladium nanoparticle cores for initiating growth of an electrolysis plated palladium layer were formed on the aperture of the nanotubes by photodeposition. After the electrolysis plating of palladium, the palladium-coated nanotubular array samples was annealed in the vacuum furnace. Then the palladium film was mechanically peeled off from the anodized titanium sheet for completing the barrier membrane, as shown in this slide. Then, photocatalytic hydrogen production and separation in the membrane were examined with a self-made measurement cell. In order to mount the membrane in the measurement cell, the membrane was glued on another titanium sheet with an aperture by using epoxy resin. Then the titanium sheet with the membrane specimen was mounted in the middle of the cell and tightly sealed with O-rings, as shown here, so that only the TiO2 part of the membrane was exposed to fuel solutions. The mixture of pure water and methanol was deposited onto the membrane, and the membrane became fully covered with a droplet. And then generated gases filtered through the membrane under UV light radiation were stored and circulated continuously by using air pump and carrier gas. Then the stored gas was analyzed with gas chromatograph. And for investigating temperature dependence, the membrane temperature was changed by controlling the temperature of a ceramic heater located underneath the membrane sample. And this slide shows the data plot of the hydrogen production amount against the duration of the UV radiation at various heater temperatures. The obtained hydrogen gas amount was proportional to the UV irradiation time for initial several hours, and an inflection point where the hydrogen production rate drastically increased was observed. Moreover, the hydrogen production rate became larger at higher temperatures. And you can see the high purity hydrogen production rate from the methanol water mixture and apparent contact yield at 90 degrees C. And now I would like to explain the mechanism of the operation of this DNA pyridine membrane. In this membrane, both hydrogen permission and adsorption process occur simultaneously at the initial stage of photo-induced hydrogen production and separation. When the hydrogen storage amount reaches the limit after the UV irradiation for several hours, only hydrogen permission is permitted on the pyridine layer, and the effective hydrogen production rate in the membrane rapidly increases, as shown here. This mechanism can be one of the reasons for the inflection points. These photoactive membranes described here and their further optimization will contribute to developing vertical compact photoreforming systems. Okay, so this is a summary of my talk. I mainly presented visible light responsive gas phase photocatalysis over the anodized hematite nanotubular arrays loaded with the Cu2 nanoparticles and photo-induced high purity hydrogen production based on the bilayer membrane of the anodized Ti2 nanotubular arrays and pyridium layer. Okay, so now I'll close my talk, and I'd like to thank my collaborators and findings, and thank you very much for your kind attention.
Thank you very much, Kay, for finishing on time. And we can have one question from audience before we move to our next presentation. If anyone has a question, you can ask right now. You can raise your hand so that I can unmute you. Or if not, you can also email Kay. The emails are in the program. So I think we can move to next presentation.
Okay.
The time is very, our presentations are very much back to back.
Okay.
The
Yeah,
next presentation is, thank you. The next presentation is by Rosario Puglisi from Consiglio Nazionale delle Ricerche from Italy. Her presentation is Advanced Doping Techniques for Non-Structured Solar Cells. So I invite you, Rosario, to start your presentation.
Okay. Thanks a lot to the organizers for inviting me to this nice conference, and and thanks to the chairperson for introducing me. As she said, the title of my talk is Advanced Doping Techniques for Nanostructured Solar Cells. I will show you a few results about the synthesis of silicon nanostructures, the development of a solution-based doping technique, and integration in solar cells. I would like to spend a few words about my institute. IMM is one of the largest research institutes of the National Research Council in Italy. It is organized in 5 different sites. The headquarters are in Catania, where I work, and then we have research units in Milan, Bologna, Rome, Lecce, and another research unit in Catania. I would like, first of all, to thank my former students and my current PhD students for the work I'm presenting today, as well as my colleague from IMM in Catania and all the universities with which I collaborate. Thanks to them, I'm presenting you these results today. In this slide, I'm summarizing the results that we obtained for the fabrication of the silicon nanowires. We have used the well-known method, which is called vapor liquid solid. It consists in using a metallic quantum dot to induce the growth of silicon nanowires at the interface between the metal catalyst and the silicon substrate. Here on the left, I'm showing you a scanning electron microscopy image taken in cross-section of an array of silicon nanostructures. And as you can see here, the silicon nanowires present the metallic nanoparticle at the top of their structure. This is a high-resolution TEM microscopy of one of them, and as you can see, they present a flat surface and their structure is crystalline. And here I'm presenting another high-resolution TEM microscopy taken on one of the smallest silicon nanowires that we have been able to grow. Its diameter is as small as 2.8 nanometer. These nanostructures present incredibly interesting properties in terms of of many applications, and growing them at such small sizes is a very challenging technological process. Now, when we want to use these nanostructures have been very, very popular in literature because we can use them as a light trapping material, if we integrate them into the emitter region of our solar cells where the device is facing the solar light, they efficiently entrap the solar radiation. So we increase the number of photo-generated carriers. However, if we want to integrate these nanostructures inside devices, we have to face a few technological challenges. The first one is creating the metallurgical junction, which is the heart of our device. So we cannot use standard doping techniques, essentially, because they have many limitations, such as the crystal damage, which is critical for nanostructured surfaces. So in 2008, it has been proposed a method which is called molecular doping. It consists in immersing a silicon wafer inside a solution of phosphorus-containing molecules. So if we want to make an N-type doping of our silicon, then we can protect the silicon and the molecules with a cap of oxide layers, and then we anneal the samples to break the molecule and diffuse the dopant atoms inside our silicon substrate. If we want to perform phosphorus doping, we use this molecule, which is called the ethyl-1-propylphosphonate, but we can go also to the P-type doping. In this case, we can use this molecule, which contains boron, and it is called the hyaluronic acid pinacolester. Here I'm showing you a few results of the electrical characterization of the samples, which have been annealed at several temperatures. And here I'm showing the carrier concentration as a function of the depth for the P-type and the N-type doping. And as you can see, we can reach peak concentration as high as 1 × 10⁻⁹ per cubic centimeter, and junction depths as shallow as 20 nanometers. But we have reached also and published 10 nanometers junction depths. So as you can understand, this method is very interesting from the scientific point of view, and the main aspect ruling the whole electrical performances is on the formation of the molecular layer. So we have followed this formation by using high resolution techniques, and we have seen that in the first deposition steps we form a complete packed full monolayer of molecules, and then we start to grow and form multi-layers of molecules, and we have been able to demonstrate that we can get rid of these multi-layers by simple treating the surfaces with chemical rinsing by using standard solvents. We have also performed DFT calculations. Here I'm showing you the results of a collaboration with Southern Denmark University, and essentially this is a schematic showing you the silicon substrate, the first molecular layer and the second one. And as you can see, the DPP molecule bond with each other through phosphorus and oxygen bonds, and they form a strong bond with the silicon substrate through the oxygen atoms, while in the case of the interaction between the second layer of molecule and the first layer of molecule, this is as has a weak nature, van der Waals type. So we integrated this process into our silicon nanowires, and this is the image of the final solar cells. We have been able to reach 9.3 milliamps per square centimeter. We still observe a strong parasitic effect due to the fact that we use the standard photolithography for a nanostructured surface, which is not the well optimized condition. Now, even molecular doping has limits, and these limits have prevented this method to have an industrial application, and this is related to the fact that standard molecules in literature essentially contain, together with the dopant atom, also carbon, and carbon can form together with phosphorus pairs of carbon interstitial and phosphorus substitutional atoms, and these pairs have multiple deep energy levels that contribute to the phosphorus electrical deactivation. So CNRIMM has recently patented the idea to use phosphoric acid as an alternative to the standard molecular structures that have been used in literature. The advantages of phosphoric acid are so numerous because it is already widely used in microelectronics factories for the removal of silicon nitride. It has a high selectivity with respect to silicon. It can be diluted in water. This eliminates the carbon presence from the solution. And also phosphoric acid is used in many foods and drinks because it improves the tangy taste in the soda drinks. So it is coming from the industrial field, and it is less harmful than standard doping materials. Moreover, it is very small. It has a small steric footprint, which means that we can pack more dopant molecules as a source on our silicon, so we can increase the dopant dose. These are the electrical results, which demonstrate that we have been able to reach a peak concentration as high as 6.5 times 10 to the 15 in terms of doses, and in terms of peak as high as 1 times 10 to the 20 per cubic centimeter. And even after cleaning, the dose is 2.2 times 10 to the 15, and the sheet resistance is as low as 31 ohms square. So I would like just to advertise the special issue, which I'm guest editing together with other colleagues on the journal Micro of MDPI. This is entitled Innovative Methods for Semiconductor Doping. I would like to invite you all to submit your latest results on this special issue, and I will leave the conclusions here just to leave to the other colleagues the time for possible questions for their talks. Thanks a lot for your attention and for listening so until now.
Thank you very much, Rosario. Because she gave us a few extra minutes, we have a chance to ask her questions. So I invite the audience to raise your hand so I can unmute you and you can ask your questions from Rosario. So we don't have a question. Probably they will reach you out through email to ask a question. So I invite everyone, if you don't feel comfortable asking your questions on live broadcasting, you can reach Rosario with email to ask your questions. And I have a question maybe about your special issue. Maybe you can tell us what is the deadline for a special issue? How many papers are you expecting?
Yeah, we have already some invited reviews, but we still have space for other reviews as well as original contributions. The deadline is supposed to be the end of September, but we will presumably shift it. So you are very welcome if you need extra time to write to us, and we will manage to ask to the publishing house to extend the deadline.
Thank you very much. I appreciate that.
You're very welcome.
So our next presentation is from University of Maryland, College Park, and the title of presentation is Laser Script Fractal Graphene Capacitors Scaling Behavior with Respect to Fractal Order and Complexity. And the presentation is given by Dr. Kaushik Das. Kaushik has already shared his slides with us, so I invite you to start your presentation. Thank you.
Thank you, Dr. Chair, and good morning, good afternoon. I know many of us are from different parts of the world. So in Maryland, this is now just noon, 12:10. So today I'll be talking about laser-scribed fractal graphene capacitors, its scaling behavior, and what does it mean by fractal behavior and what is fractal. Many of us already know that fractals are very interesting structures that we see often in nature, taking, say, for example, a fern leaf, or some intricate structures where some pattern is repeated, right? So first question is what is laser scribed capacitor, and why do we even need to use fractals, or how could we implement fractal structure in laser scribed graphene capacitors? So what we did, we created a thin film of graphene oxide on a substrate. In this case, we use glass plates as a substrate. We have tried like some plastic also, and it worked. And we used a commercial XY plotter, and then we convert it into a laser scriber using a laser head. And whenever that laser falls on graphene oxide, what it does, it knocks out the oxygen molecules from graphene oxide, and it converts into graphene. So graphene oxide is an insulator, and when a laser is used, laser heat to knock out the oxygen molecules, it converts into reduced graphene oxide, and it becomes conducting. So this is the schematic. So you on the left top, you create the thin film of graphene oxide, and then use the laser scriber using that XY plotter in a two-dimensional plane. And then you create different structures, fractal structures, and then use the analytical tools to measure the capacitance of that capacitor. So that's the scheme. And here you can see on the bottom right that there is this thin film of graphene oxide on a glass slide. And then this blue dot is the laser dot. And as the laser scribes on that thin film, that black line is actually the reduced graphene oxide line, which is a conducting line. So it immediately opens up a huge opportunity for us to use that graphene oxide sandwiched between two conducting lines, which can be used as electrode, right? So graphene oxide or some composite of graphene oxide you can use as a dielectric medium in between two laser scribe lines, and these laser scribe lines are conducting in nature, so you can create an effective capacitor, and you can create a flexible capacitor also, graphene oxide, reduced graphene oxide capacitor, or graphene capacitor, you may say. So that can it's low cost, it's very easy to make, and it could be, you can even use non-toxic biodegradable substrates to create these capacitors. So, and graphene oxide is non-toxic. It's just graphite or graphene. It's just 2D carbon molecules, right? So there is ample opportunity to use this technique. And we tried with different intensities of the laser, and we investigated the optimal values. And initially we tried, it worked, but we faced a difficulty when graphene oxide was converting into reduced graphene oxide, RGO. It was flaking off. So even if it was converting, even when it was converting into conducting graphene, it was not sticking to the substrate. So that was a problem, and we solved that problem by using some binding agent with graphene oxide. So and then there are a few issues also, like the intensity, the depth, and the speed of the laser head. So all these parameters had to be optimized, and once you optimize this on different substrates and different concentration of graphene oxide, you can start creating your capacitor. So we have also tried to see what happens if we put the graphene oxide thin film below a substrate, and if we face it up or face it down. We haven't seen any difference because laser, incident laser beam, it penetrates through the transparent substrate, in our case glass or PET, and then it can still reduce the graphene oxide films underneath the substrate. And when it is face up, there was no problem, obviously. So what happens is, when the laser hits the graphene oxide film, any moisture that it contains, it gets evaporated due to intense laser heat, and carbon dioxide gets out of it, and because of the oxygen molecule, they get out. So it combines with carbon, some carbon, it becomes carbon dioxide, and it flows as carbon dioxide gas. And these are some of the early developments of our capacitor that we created using that XY plotter. These are fractal structure, Hilbert space structures of different order. And you can see that these structures, these fractal structures, are repeating itself as we are increasing the order. At the bottom row, you can see this is the 0th order. You take an unit, and then if you repeat that unit, you get the 1st order and the 2nd order, 3rd order, 4th order, like that. So why do we even use it? This is a 2D plane. We are creating the capacitor on a 2D plane using 2D material. Now, capacitor, the basic understanding of capacitor is that capacitance of any capacitor is proportional to the surface area available to the electrons to sit on, right? Here, the substrate itself is 2D. So, and the electrons have the ability to sit on those places where the graphene line is created, right? So our goal was to maximize the 1D surface area, that is the line area, the line length, actually, for the electrons to make available for the electrons, so that you can store more charges. And one way to do that is to create fractals. So that's why we started studying fractal structure and whether there is any correlation with different types of fractal and the capacitance. So that was sort of the interest. So everybody knows that capacitor purpose is to store large volume of charge in an electric field, need for stable and fast energy discharge to conductors separated by solid dielectric. In our case, These two conductors are two graphene lines, and the dielectric is graphene oxide, right? So energy storage by the separation of charges across the two plates. And you have different types of supercapacitors. We can, here we are more interested in electrical double layer created supercapacitors. And here the anode activated carbon and the discharging model you can see here. And in current collectors link the active material to the external circuit. The electrolyte can be composed of mobile ions, ionic liquid, aqueous salt, acidic solution, gel polymer. You have plenty of choices, and the separator allows ions to migrate between the electrodes, but is non-conductive. So that those are standard practices. Our goal is to create those supercapacitors with a very low cost material, and which is not very environmentally harmful, and increase electrode surface area by introducing fractal structures in there, and use of graphene, because graphene itself is a 2D material, so its surface area is huge, right? That's why we use nanomaterials or 2D materials, because when instead of taking graphite, if we use graphene, then surface area increases enormously. So this technique actually first reported by Elcaddy and Kenner, Rick Kenner of UCLA. They used actually a very unconventional technique. They took a DVD disc, a light scribe DVD disc. And then they coated graphene oxide on the DVD disc, and then put it in a DVD burner. And in a DVD burner uses laser, and they were able to create those supercapacitors. So we took the idea from them, and then we created our supercapacitor. The different electrodes and the electrolytes that we have used, you can see it in our corresponding paper in more details. And we used PVA also, and H3PO4, and then we mixed it in geo and coated it separately, and in both cases we got good result. So we checked with like what difference does it make, the laser, and we used FTIR and Raman to see that yes, indeed the FTIR peaks show that the oxygen OH groups are reduced, and Raman shows that the graphene oxide is getting reduced to reduced graphene. So these are some of the nice pictures of our capacitors we created. These are snowflake structure, and this is a natural fractal structure in form that I have already mentioned. We used Sierpinski arrowhead structure, and the other snowflake structures. This is Hilbert arrows, and these are the different fractal structures we use: Sierpinski curve, Hilbert curve, Sierpinski arrowhead, Minkowski sausage, Koch snowflake, Koch curve, and all these fractal structures we use. And the fractal structures, their roughness is basically measured by the Hausdorff dimension, which is a mathematical number, and this dimension is actually not a prime number, or not a number which it can be a fraction. So that's why this is the name fractal came from. So the fractal dimension, unlike like 1 dimension, 2 dimension, 3 dimension, fractal dimension could be 1.2, 1.3, 2.6, like that. So we created, these are the real picture of our capacitors that we created, and and we checked the FTIR and Raman shapes to characterize them. And we created some of the measured the capacitances, and finally what we did, we plotted the fractal order with log of the fractal order with log of the capacitance to see if there is any scaling behavior we can see. And we saw that there is indeed a scaling behavior with in terms of the fractal order. So that means that most likely there are two competing phenomena, or two competing effects are going on there. One is as the fractal order is increasing, that means there is more path for the electrons to more length for the electrons to sit on or to charge. More charge can be stored in there, but at the same time, the path length introduces some resistance, internal resistance. So these two competing effects, that's our hypothesis. That's why we see this scaling behavior. And the capacitance was not very high in our case, because that was just a proof of concept. We are still continuing to work on that, and we are planning to use some other etching techniques, other conversion techniques. This was just a very crude, very simple technique we wanted to demonstrate that you can use. But in the next step forward, we'll try to maximize the capacitance of the capacitors. So this work was partially supported by National Science Foundation, Department of Education, and Maryland Technology Enterprise. And I'd like to thank them and thank you all for your patience. And I'm open for any questions. Thank you.
Thank you very much, Kaushik. If we have any questions, we can quickly go through that, or you can reach out to Kaushik by email for more extensive questions. On the timing, we are getting ready for our next presentation. Next presenter is Mohammad Mehdi Keshavarzi. He's actually my PhD student, and he will be talking about detailed multiphysics modeling of an 18650 cylindrical lithium-ion battery. That's the research we have been following in Temple University Electric Vehicle Safety Lab, and he will be talking about that. So Mohammad, you can start.
Hi, can you hear me right now?
Yeah.
Hi everyone, thank you for joining my presentation today. I'm Mohammad Keshavarzi. I'm going to talk about the detailed multi-physics modeling of an 18650 cylindrical lithium-ion battery, which is an ongoing project between Electric Vehicle Safety Laboratory at Temple University and Research and Development section of the Dassault Systems Simulia Corporation. So these are the headlines of my today's presentation. I'm going to do a brief introduction first, then I'm going to talk about the 18650 cylindrical lithium-ion battery, which is used in this study, and how we extracted the geometry and how we created the model. And then I'm going to talk about the mechanical tests that we did on the components and also the whole cell of these 18650, and how we did the same procedure in the simulations to validate our mechanical model. In the next step, I'm going to talk about the electrical tests that we did on the components of this cell and how we used our previously well-calibrated mechanical model in these electrical simulations as well. And then at the end, I'm going to wrap up with the conclusion and some future steps. So right now, in this electrification era that we are living right now, we are surrounded by lithium-ion batteries, but still we need them to be more powerful, smaller, to take us further down the road or more up in the air. But at the same time, we wanted them to be safer since we are all surrounded by these batteries and we do not want them to be catch on fire wherever we are. So these escalating demands for better batteries are forcing all the researchers to do numerous studies on different types of lithium-ion batteries. To name these different types, we can name pouch cells, elliptical cells, cylindrical cells, and prismatic cells. In this study, we investigated the most common type of electric vehicle, common type of lithium-ion batteries which are used in the electric vehicles, which is these 18650 lithium-ion batteries. So what I'm going to talk about today is the multi-physics detailed model of 18650. And why we are doing it is that numerous studies has been happening on different aspects of these lithium-ion batteries, naming them investigation of the electrochemical properties, thermal properties, electrical properties, and even the mechanical properties. But as we look at the whole cell, we see lots of complex phenomena happening at the same time, which are coupled phenomena. So understanding these coupled phenomena has really great importance for all the battery industries. So our final goal in this project is to create a universal detailed model which would be capable of in all the mechanical, electrical, thermal, electrochemical simulations, and most importantly in the coupled effects that they have on each other. For instance, in the mechanical damage, the mechanical damage in a lithium-ion battery can induce thermal runaway, or it can change the electrochemical properties, or it can decompose the materials inside the batteries. So understanding these effects has great importance for everyone in the battery industry. Another goal and feature of this model can be used as a tool to go from detailed to homogenized model of these batteries, which eventually reduced the computational cost significantly. So how we are going to do it is building this detailed model. First, we have to characterize the geometry of the cell by the CT scans that we had to create the whole cell model, the top covers, the jetty roll, the components, the bottom of the cell, everything is done with the CT scans. And then in the next step, we have to calibrate the material properties to get the best results. The material properties should, for each of the layers and each of the components, should be tested separately and validated separately. And at the end, we validate our model in various loading scenarios, which are mechanical, thermal, and electrical simulations. So let's talk about the geometry of the casing of these batteries. As you can see at the top, we can see the CT scan of these 18650. We can see the shell casing, we can see the top cover, the thicknesses, everything, the location of the jelly roll inside the lithium, these 18650, the location of the tabs, the geometry of the bottom of the cell, everything can be seen and measured from the CT scan. So we did the CT scan of these 18650 and we created the same casing model with the exact measurement of the thicknesses that we got from the CT scans. As you can see, the location of the tabs are also important in the modeling of these 18650 that we could get it from the CT scan, and also the jelly roll inside these 18650, which consists of 4 layers of anode, separator, cathode, and another separator, which are rolled all the way in a spiral configuration to form the whole jelly roll which is inside the lithium-ion batteries. So we created the model of these 18650 based on the reality and the exact measurements of the CDS scan that we have for these battery cells. But that was the geometry of the cell. Let's talk about the material properties and how we extracted the material properties of these cells. First, we conditioned one of our cells at Temple University. We discharge the cell, we open the cap, we extract the jelly roll from the shell casing. And as I said, the jelly roll itself consists of 3 main layers: cathodes, anode, and separator. So we created samples of these cathode, anode, and separators when we did a bunch of testings on these components. These tests were tensile tests and compression tests. For the tensile tests, for our samples, we clamp them at both ends and then we pull them to extract the load displacement of each of the samples. And for the compression test, we stack them all together and then we compress them between 2 flat plates and we extract the load displacement data from these tests as well. To build the same model for the layers in Abacus, what we did is to use 3 layers for the anode and cathode, which is realistically based on what we see in the layers. We have 1 current collectors, which is usually copper for anode and aluminum for cathode. And we have double-sided coatings for these electrodes in the commercial batteries. For the separator, which is usually polypropylene material, it is a porous material. We use the single layer. For the electrodes, which are cathode and anodes, for the coating properties, we used material crushable foam, and for the current collectors, which are metal structures, we use elastic plastic materials in the Abacus. For the separator, we chose anisotropic in-plane properties. We use honeycomb material. So to briefly describe what is behind these materials, and the crushable foam material, it is following the Despanda-Fleck model. The Despanda-Fleck model uses the yield surface evolution, and for the honeycomb model, the Abacus model gets the stress strain values for the tension and compression. The tension part is in the positive strain values and the compression part is in the negative part value. So we calibrated these crushable foam and honeycomb material for each of the layers, and we built our jelly roll based on the validated result, based on the calibrated results of these layers. So we wanted to validate our testings as well. So what we did in Abacus, we did the same procedure for our tensile test, which meaning that we pulled each of the layers at both ends and extracted the results from the software and we compared them to the tests that we have. As we can see here, the load displacement data of the layers are following the same trend. We did the same thing for the compression test as well. So we stacked the layers in the simulation software and then we compressed it between 2 flat plates as well. And as we can see also here, the components in the compression are also validated. So by this means, we are confident that our layers are calibrated calibrated individually, but we wanted to make sure and then try to simulate the whole jelly roll model inside the whole jelly roll and how to see how it is reacting when we are doing the simulation on the as well. So at Temple University, we extracted the jelly roll and then we compressed it between two flat plates as well. We did the same thing in the simulation. So this is the whole jelly roll which is compressed between two flat plates. As we can see here, the experimental results, the simulation results is very well following the experimental results. In the next step, we put the jelly roll inside the cell case, the casing of the battery. So as you can see here at the bottom of this page, we have the whole cell model, which is compressed between two flat plates. And we did the same experiments on this cell, and the cell and the experiment, the experiment and the simulation are following the same trend as well. So by this means, we are well confident that our mechanical model is well validated, and we went to the next step. The next step for us was to measure the electrical conductivity as an input for the Abacus software. So if you look at the literature, there are a wide range of electrical conductivities for the cathode anodes, and because the composition of the electrodes are a trade secret for the companies, everyone that wanted to do a simulation should measure the electrical conductivity of the layers by themselves. So what we did is that use a silver paste for each of the layers in different configurations, and we swapped current for each of the silver paste that I attached with a wire, as you can see in this picture. And then I measured the electrical conductivity of the layers, which we used it in Abacus software for our simulations. So for the electrical modeling, we connected the bottom of the cell to the electrical potential of 0 and the top cover to the electrical potential of 3.65, which is the nominal voltage of the cell.
40, if you can please wrap up.
Sure. So we could see the electrical potential in the flowing through the jelly roll, and we can see the electrical potential in the tabs. And that was the electrical modeling. So to wrap up, we know that the batteries are multifunctional materials, that each of the layers should be calibrated separately and based on reality. The detailed model of our model do mechanical.
Thank you, Mohammed. I think we have to move to our next presentation.
Sure.
We don't have time for questions. You can send questions to Mohammed by email. Our next presentation is by Dr. Wing Chang Tsui from Swansea University, United Kingdom. And the title of the presentation is Organic Photovoltaic Devices for Next Generation Indoor Applications. So I invite Dr. Wing Chang Tsui to start his presentation. Thank you for being with us.
Hi, can you see my slide and hear my voice?
Yes.
Thank you.
Yes.
Thank you. Right. So my talk is about organic photovoltaic devices for next generation indoor applications. So first of all, I would like to mention about what is indoor PV. So it's very simple. It's like solar cell, but instead of using outdoor sunlight, we use indoor lights like LED or fluorescent lamp. So you can see some examples here. And the main difference is that the spectrum, the light spectrum, is mainly in the visible region for this indoor light. And this is a big difference, and it will affect how to optimize the performance. Yeah. So the motivation for indoor PV can be classified to two groups of application. One is more like power low consumption electronic devices, like the traditional calculator, right? You can use the, even nowadays you have a small PV panel, solar panel here. And more latest is on the watch, integrated on the watch, and wireless keyboard. But the other more interesting application is the Internet of Things. And this is basically some electronic devices which you can use sensors to detect, for example, the temperature, the humidity, and then it can transmit the data to a PC or the mobile phone. And it's a very popular topic, and it's a very rapidly going technology. And the sensors normally only require very small amount of power. So even the power generated by indoor lights could be sufficient to power the Internet of Things. So this is a very interesting topic. And about the status of indoor PV, traditionally, like the outdoor application, silicon solar cell is dominant, and probably the only product at the moment, commercial product. And similar to outdoor application, 3.5 solar cell has high performance, but again, the problem is could be much more expensive. So we think about if there's any potential material, which PV material, which can has high performance under indoor lighting, but at the same time low cost. And based on this, we think organic PV material could be very interesting for indoor application. And the reason behind include the absorption of the organic semiconductor can be tuned easily by chemical method. And so you can tune the absorption to absorb more in the visible light, which is the main light spectrum from LED or fluorescent lamp. And the other interesting thing is about the potentially low cost production, because this organic semiconductor can be solution processed at low temperature. So you can see here a photo about the possibility to make it using roll-to-roll printing or coating method. And it could lead to new applications as well, because they can be deposited on flexible lightweight substrates like this photo. And like this photo. So it can be integrated to an electronic device which has a curved shape. So last but not least, the stability issue could be better under indoor lighting. So one of the main issue for this kind of organic semiconductor for solar cell is the stability. They're not that stable. But under indoor condition, the light normally doesn't contain UV light, much lower intensity than outdoor sunlight, lower temperature, not exposure to like rainfall. So it's expected to have much better stability than outdoor application. So now I start to show some example about our work on the indoor performance. So you can see here a figure of the current density versus voltage curve for the three different types of organic solar cells. And you can see the efficiency is not that high under this one sun AM 1.5G outdoor type of spectrum testing. But if we use the fluorescent lamp under 300 lux, which is a typical light level, like in the office, and you can see that the efficiency is about double than the efficiency under outdoor light spectrum. And this is very interesting, and the reason is because this material absorbs more in the visible. And so the band gap for this material is around 1.8 to 1.9 eV, particularly for this semiconductor. And so this band gap is matched very well for the indoor light spectrum. And you can see the best performance here. We got about 12% efficiency under indoor 300 lux illumination. And this efficiency is already pretty comparable to silicon solar cell for indoor application. So this data show it could be promising. The organic semiconductor can be promising for indoor application. And the ideal band gap theoretical calculated for indoor application is around 1.8 to 1.9 EV, and this material can be tuned to this band gap. And you can also see the open circuit voltage here, right? It's pretty high. So and this is one of the requirements when go to the indoor light application, because normally the VOC will drop, the open circuit voltage will drop with lower light intensity. So so in order to keep a good open circuit voltage under low light, the VOC, the initial VOC need to be high, and it shouldn't drop that fast with lower light intensity. So this was published a few years ago, and it accelerates the researcher in our field to do more research in this area after this publication. So a couple of years ago, we start to find out the right material for this application based on the requirement of the band gap, the high VOC under one sun, and then we found a material, small molecule organic semiconductor, and as the donor material, and work with a fluorine acceptor. And you can see that here is the external quantum efficiency spectrum of the solar cell under different solvent vapor treatment. And the red one here is the light spectrum from the fluorescent lamp. So you can see that the EQE is very high within this spectral region, and the optimum device have very high EQE at this emission peak from the fluorescent lamp. So the efficiency under 1000 lux fluorescent light is around 20%, and this is much better than silicon. So we show that the organic semiconductor could be very promising for indoor application compared with silicon. And here's a summary, and I'll provide a bit outlook. So in summary, you can see that the organic PV, the green one here, is much higher performance under indoor light than the silicon, and it's comparable to the gallium arsenide, which is more expensive. So it's already very good performance under indoor lighting. And this is a figure about the maximum power output versus year. So you can see for organic solar cell OPV, there are more and more research after our first publication, which showed they could be promising for indoor application. And you can see the performance nowadays is keep improving. I think the latest one is over 30% under 1000 lux LED light. So for the outlook, I think upscaling is very important. They're still in a small devices, and The good thing for indoor application is it may not need that big area to generate the power required. Stability, although it should be very good compared with outdoor, but there's not much study in this area. So you need more study in this area. And prototype device, which I mean to integrate with sensors to see how good it works and how to optimize the electronics. And finally, about the standard for testing. So there's no standard for testing the efficiency for indoor application. So people reporting different efficiency and we don't know how to compare it. So we are also working in this area as well. So finally, I just want to acknowledge the Welsh government for the funding for this work and the people at Swansea University, the collaborator at Imperial College and the National Physical Laboratory. Right, thank you.
So thank you very much, Dr. Wing. We have 1 minute left for this talk. So if any of the audience have any questions, I invite you to raise your hand to ask a question you have from Dr. Wing. Okay, I don't see any raised hands, so please feel free to reach Dr. Wing with email and ask your questions after the session. So we will move to our next presentation. Thank you very much.
Thank you.
From our presenter. And our next presentation is by Mr. Mir Musavi from Tarbiyat Modares University. The title of Mir's presentation is Negative Electrode Materials for Supercapacitive Energy Storage, Bottlenecks and Possible Remedies. Mir, and I invite you to start sharing your presentation with us, and you can start presenting. Okay, seems we have technical issues. I see Mir is in the session, but we cannot see his presentation. So I will start the video that he has shared with us, so we can enjoy the presentation through the video.
Hello. Ladies and gentlemen, and I appreciate the organizing committee for managing this outstanding. The main bottleneck of supercapacitors is their low energy content. As you know, the energy of supercapacitors, two important parameters determine the amount of
Hello, Dr. Mir Fazlullah.
Hello, hello.
Can you please start your presentation?
Okay, okay.
Please share your screen.
Okay.
Thank you so much.
Just a moment. So is it shared? Excuse me, do you hear me?
We hear you and we see your video, but we cannot see your presentation.
Okay. So is it shared now?
No, it's not.
Not?
No.
Oh, what is the problem? I click share, but I don't know what happened.
Yeah, right now it is, yeah, it was showing your screen.
Okay.
But yeah. Yes, now it is showing your screen.
Okay.
Maybe you can move to the slide that we were showing to continue from there.
Okay. Ladies and gentlemen, thank you for joining us. I appreciate the organizing committee for managing this outstanding meeting. My talk title is Negative Electrode Materials for Energy Storage, Bottlenecks, and Remedies. As you know, supercapacitor has a high power device, suffer from relatively low content, low energy content. The low capacitance of negative electrode materials severely limits the device capacitance. The most efficient negative electrode materials are carbon-based materials that operate based on the EDLC mechanism, and their capacitance barely exceed 300 farad per gram. In this study, we functionalize graphene with a thionein as a fast kinetic organic redox active species to fabricate high power, high energy device. As you see, it provides 93% capacitive behavior. That means with increasing the energy storage capability, its power almost retained, not sacrificed. Here, you can see a schematic illustration of preparation of thionein functionalized 3D graphene aerogel nanocomposite. As you see, we prepared very lightweight, floated on the top of the solution, and a leaf can easily tolerate its weight. This slide shows the characteristic of the prepared metal-free device. As you see, it includes wide voltage window, 2.1 volt, and excellent performance, bendable, electrical application. We use the upgrade for 5 minutes. In another study, we prepared the Nile blue functionalized graphene aerogel electrode that displays excellent supercapacitor performance in the negative potential range. This figure shows the electrochemical study of prepared composite at different electrolyte. As you see, it covers whole spectrum of pH of aqueous electrolyte. This slide shows the performance of fabricated device. In all devices, the prepared composite serves as negative electrode, the same negative electrode, but different positive electrode. In another approach, we were inspired by the strong adhesion properties of muscle in which the catechol and amine moiety responsible for their adhesion properties. So we selected dopamine that contain both the catechol and the amine moieties, and the prepared polydopamine supported on oxygen functionalized carbon-close supercapacitor. This slide shows the fabricated process of muscle-inspired electrode. After functionalization, we employed the electrochemical method, pulse potential pattern, for electropolymerization. We fabricated all solid-state, metal-free device and evaluated its performance, including the operating voltage and capability of the device. Okay. We also studied the other characteristic of device, including cycling stability, flexibility, conductivity, and comparison with other devices. Highly stable, bendable, and good electrical conductivity. Okay. What's shown here are the practical application of prototype device in deriving a rotor and lightening up LED. In another study, we employed hard template SPA15 for preparation mesoporous carbon and then composite with CO and prepared MCNCA nanocomposite. It is very lightweight also. These images clearly show that the MCN adopts the SPA15 template shape and the honeycomb view. Sorry. PET and the BGH analysis confirm the mesoporous structure of MCN and its composite. electrochemical evaluation of the prepared device shown here, the performance of composite much better than MCN alone. Aside from the carbon-based material, which are well-known family of the negative electrode active material with most EDLC-like characteristic, some metal oxide also provide capacitance in the negative potential range. This slide shows the potential window of some metal oxide. Green bars shows negative electrode active material, orange bar show positive electrode active material. On the hunt of negative electrode active material, we also prepared two bimetal oxide shown here, cobalt iron oxide and also copper cobalt oxide.
We are at the end of the designated time. If you can please wrap up the presentation.
Okay, just let me, we prepared via a very simple method we developed in 2013. And this is performance application. Let me acknowledge my collaborator, co-workers, Professor Kainer, Dr. Maher, Dr. Rahmanifar, our team, especially Dr. Nouri, Professor John, and thank you very much for your kind attention. Thank you so much, and sorry for some problem in the starting.
Thank you very much for your presentation. Unfortunately, we don't have time for questions, but I invite all of the audience to contact Mir with your questions with email. You can be in touch after the meeting. We are getting ready for our last presentations. Mir, maybe you can stop the sharing. So our last.
Okay. Thank you so much.
Thank you very much for joining us and your presentation. So the last presentation is by Dr. Elena Rushkova from Oregon National Laboratory. And the title of the presentation is Merging Nanotechnology and Synthetic Biology Toward Directed Evolution of Materials for Photocatalysis. Elena, thank you for joining us, and you can start sharing your presentation. Elena, you are still mute. Yeah, now we can hear you. You're mute now. We still cannot hear you.
And also chlorophyll independent, regional centered, minimalistic system of proton pump in bacterial reduction used by Archi when only proton gradient is produced and utilized by ATP synthase for synthesis of ATP. In 1972, Fujishima and Honda in their pioneering work published in Nature reported artificial photosynthesis, namely photo-assisted electrochemical water oxidation on N-type titanium dioxide working electrode and metal counter electron under UV light irradiation. If we now imagine if we bring together very close to each other semiconductor and metal nanoparticles in one hybrid nanoparticle, we are coming to the area of photocatalysis, which is the subject of my talk today. Recently, semi-artificial photosynthesis was introduced. It's in fact nanotechnology boosted examples of biotechnology when semiconductors or gold nanoclusters are utilized to provide energy for non-photosynthetic bacteria, or then enzymes also are boosted with nanoparticles and to provide photoinduced electrons for their activity. In our research, we are inspired by biological phenomena, and we combined a variety of approaches, including chemical synthesis, microfabrication of inorganic materials, combine them with biological entities obtained via synthetic biology or isolated from biological sources using classic biochemical techniques. We utilize all these approaches for directed materials evolution toward new functions, very often with no examples in biology. So as I mentioned before, proton pump mechanism is based on only one protein. It's a small 26 kilodalton transmembrane pore centered with cofactor regional, and whole entire process of proton pumping from cytoplasm to extracellular space is a light-induced mechanochemical process or initiated through photoisomalization of regional. So formed proton gradient is utilized by modern protein ATP synthase or synthesis of ATP to ATP from ATP. So once proton pumps of bacterial rhodopsin assembled into natural membrane, they form naturally occurring 2D crystal lattice, very neat architecture with excellent properties at varieties of high temperatures, pHs. They are stable to multiple photocycles, and these are very, very good material to construct nanobioassemblies. Majority of our nanobioassemblies for solar energy conversion are based on this energy diagram. Upon light radiations, electrons are excited from HOMO to LUMA and then injected to the conduction band of the titanium dioxide due to the energetically higher excited state of bacterial rhodopsin. So in our previous works, we demonstrated that membranes, patches isolated from halobacteria, can be directed, assembled with clusters of titanium dioxide, P25, doped with tiny platinum centers up to 5 nanometers inside. And this, such systems, they efficiently produce hydrogen at neutral pHs and in water in presence of sacrificial electron donors. And we demonstrated that bacterial rhodopsin serves as a dye-synthetizer to visible light of titanium dioxide, and also proton pumping is very important, most possibly for stabilization of chair-separated carriers. Since we are using transmembrane proteins, and traditional biochemistry and protein engineering of such proteins is quite a challenge, we started looking how we can produce more biological structures with control properties. So we came to synthetic biology as a toolkit for directed evolution of energy materials. While a major field of synthetic biology is dealing with top-down approach, when cell is function is rebooted by using synthetic DNA, and cell serves as manufacturing facility, we are focused on bottom-up minimalistic approach of new materials development using synthetic DNA and artificial membrane. So therefore, we used assembled synthetic membrane or nanodiscs developed in Urbana-Champaign in group of Professor Sliger. These nanodiscs assembled from lipids and scaffold protein with controllable diameter. So this disc can be directly combined with energy supply and ATP, isolated ribosome complex, and also building blocks such as amino acids, cofactors, retinol, for example, and synthetic DNA coding transmembrane protein. So within hours, we can produce completely functioning, properly folded protein. So here you can see atomic force microscopy image of nanodiscs before and after protein expression. You can see how they diameter and height changed upon protein expression. And these discs could be isolated and directly assembled with semiconductor nanoclub. So when we compared hydrogen evolution reaction using synthetic bacteriorhodopsin nanoparticles, soft nanoparticles, we obtained a much more pronounced photocatalytic activity compared to carrier. So we can try to explain it by the fact of more controllable structures and sizes of soft nanoparticles comparing to micron scale structures, patches. So, and also our approach allows for more sites for water molecules for interaction with nanohybrid. In our next work, we decided to switch from slurry or nanobiohybrids in bulk solution to confined space or container. So, and we made the artificial protocell. So if you compare with biological cell, which model is composed of lipids assembled with transmembrane structures with some DNA and organelles inside. So in our artificial cell, the wall is constructed from inorganic nanoparticles assembled with transmembrane proton pump. So we started, we made colloidosomes starting from silver gold nanorods, assembled two plasmonic colloidosomes. It's a kind of 3D supraparticle compartments, and we assembled bacteriorhodopsin purple membrane on the top. And asked why we decided to use plasma nanoparticles to build the wall. The reason for that is that natural photocycle of bacteriorhodopsin includes multiple intermediates, and half of cycle is fast reaction and another part of cycle is slow reaction. when retinol is going thermodynamically back to ground state. So our idea was to use broad plasmon resonance of gold-silver nanorods overlapped well with the absorption spectra of bacteriorhodopsin and this intermediate 412 nanometers. So idea was how to accelerate a natural photocycle of bacteriorhodopsin and making proton pumping more efficient. So you can see here the sums and a more passive transfer of small modes, just multi-wall structure. And here, the last one, these are colloidosomes assembled with cells. And if we compare the hybrid colloidosomes with proteoliposomes containing ATP synthase and demonstrated ATP synthesis, and again we show that proton pumping activity was sufficient for signaling of two artificial proteoliposome to produce ATP. So we decided to mimic CO2 reduction for the system via proton-coupled electron transfer. So as it's known that direct production of anion radical from CO2 is thermodynamically difficult reaction. However, through proton-coupled electron transfer, we can easier obtain products of CO2 reduction. However, in this case, we are going to need more protons and electrons. For example, to produce carbon monoxide, we need 2 protons and 2 electrons, while once we want to get methane, we need 8 protons and 8 electrons. So we started from hollow bacteria, isolated purple membrane, and then we reconstituted them into lipid vesicles. This step is very important for control of direction of protons. So instead of P25 clusters, we synthesized a mesoporous hollow titanium dioxide doped with palladium particles, since palladium is preferable for CO2 reduction over hydrogen evolution reaction. And then we fused all of this to a semi-artificial photosynthetic, and then so proton-related production of CO and methane CH4 by our biohydrogen system. So it's important that at the beginning, at the first couple hours of this reaction, the main product was CO, while after hours of reaction, the main product was methane. We can offer to explain it with the fact that CO2 reduction to methane requires much more for the induced electrons, and for the induced protons combined or met in confined space of our nanohybrid. So then come to entirely new function. For example, in case of proton pump, once it's combined with inorganic structures, its natural photocycle can be enhanced, or it can start participating in hydrogen production or CO2 reduction reactions to value-added chemicals that does not happen in nature. So from biological inspiration to new materials. Thank you for your attention.
Thank you very much, Elena. We are at the end of our session for functional materials for energy storage and conversion, session 2. Because we don't have any other presentation, next we can give time to audience. If you have questions from Elena, you can ask it now. You can raise your hand so I can unmute you. And of course, the option of sending her an email.
I think the session went over. Actually, this is the next session should be should have started at 1:20, and it's the same room.
Oh, it's the same room. Okay, so we have to thank everyone for their presentation. Thank you so much, and we say goodbye and hope to see you in future sessions. Thank you. Bye-bye.
Thank you.
Thank you, Dr. Ilham, for chairing this session, and welcome Dr. Mia Fan to chair our next session. Please, you can proceed now. I will change the name of the session.
Yeah, thank you. And I think we should start. So this session is already 10 minutes late without starting, and I think we should just go ahead and start. So our first speaker is Pavel Choshin. And could you put your presentation up? Oh, yeah. That's great. And please, the platform is yours.
Thank you very much for your kind introduction. Can you hear me well? Can you hear me well? Okay,
yes.
Great. So I will speak about the origin of the light-induced phase segregation and mixed halide perovskites. You know that perovskite photovoltaics is quite a promising emerging technology, and the current best certified efficiencies for perovskite solar cells, they hold beyond 25%. And since perovskite solar cells can be produced using solution-based techniques, the target price of perovskite solar panels is estimated to be lower compared to the mainstream silicon PV technology. And therefore, currently, only the short operational lifetimes of perovskite solar cells limit their practical implementation. There are many aging pathways which were revealed for perovskite solar cells, and there are a lot of approach designed to mitigate this kind of aging mechanisms. And among them, I believe light-induced halide phase segregation is one of the most important, because mixed halide perovskites currently show highest photovoltaic efficiencies. And the second reason is that mixing halide anions is required to optimize the bandgap of these perovskite absorbers for tandem devices, for instance, with crystalline silicon subcells. How do we observe a light-induced halide phase segregation? The easiest way is just to monitor the evolution of the emission spectra of the mixed halide perovskite films and the continuous light exposure. And what happens typically is that original band of the mixed halide perovskite, it goes down, and a new band appears at lower energy. And this is due to the formation of iodide-rich and bromide-rich domains. And since iodide-rich domains, they have the lowest bandgap, they emit at the lower energy. And when we switch off light, everything just goes back. So these phase segregated domains, they intermix and they regenerate initial mixed halide perovskite. There are many debates on the mechanism of this very interesting phenomenon. And we also addressed this challenge in our recent paper, and we investigated two model systems, all inorganic cesium-lead bromide and iodide. I will call it stoichiometric perovskite, and another material which has excess of cesium bromide, which we have shown before, is improving the electronic property of the materials and also enhances its photovoltaic performance and photostability. So we, first of all, we investigated PL dynamics for these two materials, and we have shown that both of them undergo light-induced phase segregation, as you can conclude from the evolution of the emission spectra. So there is this new low energy band which is appearing under illumination, and it's disappearing when the material is left in the dark. And what is interesting is that non-stoichiometric material undergoes much faster dynamics which is due to the presence of this additional cesium bromide. Then we investigated long-term aging behavior of these two materials, and we have shown that stoichiometric perovskite degrades with the formation of cesium lead bromide, the perovskite phase, and cesium lead iodide, which was formed in this case as non-perovskite yellow orthorhombic phase, and some other impurities. And if we look at the behavior of the non-stoichiometric material, first of all, we could notice that its complete degradation requires like 10 times longer light exposure, and the composition of the products is different. So we form cesium lead iodide, which is the same product, the perovskite, while cesium lead bromide. While cesium lead iodide in this case is formed as a black cubic perovskite phase, as you can conclude from the evolution of the XRD patterns and the appearance of this low energy absorption tail in the optical spectra. So we have quite an interesting situation when two very similar materials degrade with the formation of different sets of products. Orthorhombic yellow phase of cesium lead iodide is formed in one case, and a black perovskite phase of this material is formed from non-stoichiometric perovskite. And since these two phases of cesium lead iodide have different electronic properties and in particularly different work functions, this was a key for interpretation of the results of in situ atomic force microscopy study, which we performed for these materials. Here you see the movie, which was built based on the results of our measurements for thin films of the perovskite exposed to light directly on the microscope stage. And what you could see is the formation of these new domains at the grain boundaries of the original mixed halide perovskite. And we have shown that these new domains, they have work function, which corresponds to the cesium lead iodide. So it's iodide phase, which is segregating from the grain boundaries of, from the grains of the mixed halide perovskite. So iodide is expelled from the mixed halide perovskite material. And this conclusion is consistent with the previous report coming from Prashad Kamat group, when it was shown that mixed halide perovskite film immersed in dichloromethane is expelling iodide in the form of actually 3 iodide anions. And this is actually the pathway which was proposed in this work, but we believe that if we form molecular iodine and 3 iodide, then the second product has to be not PbI2, but metallic lead, just to preserve the stoichiometry of the system. And this kind of aging pathway is not surprising because we revealed this kind of degradation for methylammonium lead iodide and a number of other perovskites. And if we assume this chemistry going on in the case of all inorganic material, then under the light exposure, first of all, we form the defects, metallic lead and 3 iodide. Then these defects are expelled to the grain boundaries, accumulated at the grain boundaries, and start to react back. It's known that metallic lead reacts with molecular iodine and with 3 iodide, reforming PbI2 and also reforming the perovskite pure iodide phase. And when we accumulate this pure iodide perovskite phase at the grain boundaries, at some point it starts to nucleate and form new grains at the grain boundaries, which we observed experimentally. I want to emphasize that we evidenced the formation of metallic lead and PbI2 in trace amounts by XRD and also by XPS. So we verified all the components of the proposed pathway. So I want to conclude that according to our results, the perovskite photolysis to metallic lead and 3 iodide and the formation of a pure iodide perovskite phase at the grain boundaries is actually responsible for the light-induced phase segregation. While in the dark, intermixing of bromide-rich and iodide-rich phases is driven simply by the entropy gain. So this kind of simple mechanism, it accounts for all experimental findings reported for light-induced halide phase segregation and perovskites, and it also explains a range of other phenomena which were documented for different perovskite systems. At this point, I want to thank my colleagues who contributed to this study, funding agencies for financial support, and you for your kind attention. I would be happy to answer your questions.
Thank you, Paul, for keeping it in time. Any questions? We have 1 minute for question? If not, I think our second speaker will be the same speaker. So we can, if you have questions for this presentation, you can also ask afterwards. Pavel, could you please put your second presentation up?
Can you see it now on the screen?
Yes, yes, we can see very well. Yeah, thank you.
All right.
And
All right.
I won't introduce you again. So please start your presentation.
Thanks again for your introduction. And in my second talk at this conference, I want to speak about energy storage, and I will focus in particular on organic redox active materials for high capacity and high rate potassium batteries. I want to remind you that most of the energy is globally produced by combustion of the fossil fuel, and there is an urgent need to switch to renewable energy if we want to mitigate the climate change or enable sustainable development of our society on a long-term perspective. However, renewable energy sources, they suffer from severe variability in time, and usually the energy generation does not actually match the energy demand, as shown here for photovoltaic panels. So you see that energy production is peaking in the middle of the day, while the energy demand is peaking in the morning and in the evening. And there are also huge seasonal variations in the and mismatch between the energy production and energy demand. Therefore, if we want to operate energy grids in a stable way with any kind of considerable contribution from renewables, we need to provide high capacity energy storage connected to the grid, which will be smoothing this kind of variations. Unfortunately, economically efficient ways to store large amounts of energy are based now only on very simple physical principles like pumping water or compressing air. And this kind of storage can be realized only in the in certain geographic locations when we have, for instance, mountain lakes or some abandoned mines where we could implement this kind of storage. However, the amount of these locations is clearly insufficient, and we want to be independent on a geographic location. So we need to find some scalable battery technology which could provide the desired capacity which is required to implement renewables. And I want to emphasize that lithium-ion batteries shown here, they are currently a bit too costly for this purpose. However, if you look at the cost analysis for lithium-ion batteries, we could see that regardless the type of the technology, like almost half of the cost goes for cathode components. So if we want to reduce the cost of lithium-ion batteries, we need to design some cheaper cathode materials. And this is the first approach, and the challenge can be addressed by replacing expensive oxides or salts of transition metals, sometimes precious ones, with cheaper organic materials. And second, we could replace lithium, which is costly by itself, with much cheaper sodium or potassium. And I want to emphasize that replacing inorganic cathode materials with organics cannot just help to solve the cost issue, but could also lead to tremendous improvement in the performance of the batteries, as you can conclude from this very simple example. So even the simple lithium salt of hydroquinone could provide like more than 2 times higher specific capacity compared to lithium iron phosphate, which is a common cathode material of commercial lithium ion batteries. And even if we go to potassium salt of hydroquinone, we could keep the specific capacity close to 300 millimoles per gram, which is among the highest reported for inorganic cathode materials. So you see the potential for organic materials, and now I want to share some of our recent experimental data. And in one of our recent studies, we utilize this very well-known hexaketone, which is trichinoyl, as a versatile precursor for synthesis of an array of low molecular weight and polymeric redox active materials. You see some structures at this slide. And these materials demonstrated quite decent electrochemical performance, so we could reach specific capacities ranging from 200 to almost 400 milliamp hours per rem, decent rate capability, and quite nice cyclability. You see no capacity degradation for more than a few hundred cycles, sometimes for 1,000 cycles. The potentials of these materials are not really high, so they are more suitable as anode components of the batteries. And somewhat higher potentials could be obtained using, for instance, covalent organic frameworks based on these 3-triazophenylene units. And using this kind of material, we could achieve equally good performance in lithium, sodium, and also potassium batteries. So you could see that for all types of batteries, we could have specific capacity above 200 milliamp hours per rem, quite good rate capability, and very nice charge-discharge cycling stability. So, for instance, potassium batteries show no capacity fading after more than 4,000 of charge-discharge cycles at high current density. Still, further improvements in the energy density require some high voltage organic cathodes, and these high voltage cathodes are usually based on aromatic amines, and in particular, this material. It's a polymer. It was introduced recently by a Chinese group as a component of the cathode material of lithium dual-ion battery. We optimized the synthesis of this material and used it as a cathode component of potassium battery, and we achieved discharge potentials close to 4 volts and quite nice rate capability, and the energy density achieved for this cathode material was coming close to 600 watt-hours per kilogram in our first report, and it was going beyond this value in our second report. And you see that this kind of organic cathode, it delivers the high energy density compared to all other types of inorganic and organic cathodes reported so far for potassium batteries. Additional optimization could be done on the anode side, and in particular, we could follow the approach introduced recently by John Houdinap group. And the key idea is using liquid sodium-potassium alloy impregnated in carbon paper as safe and very stable anode. Why is it safe? Because liquid metal cannot form dendrites. You know that most of the safety problems arise in metal-ion batteries arise due to the dendrite formation. In this case, it's simply impossible because metal is liquid and it's self-regenerable anode. And therefore, we could cycle these batteries at really harsh conditions at the current densities going up to 50 amperes per rem. And both polymeric cathodes could sustain this kind of operational regime. And if we look at the performance of these devices in terms of energy density and power density, you could see that they can be favorably compared with a number of other metal ion technologies and also the supercapacitors, because we could have specific power going beyond 10,000 or even up to 100,000 watts per kilogram, which is actually supercapacitor operational regime. At this point, I want to summarize my talk, and the first message is that a family of new low molecular weight and polymeric materials was designed, and some of these materials were shown to be promising anode components for potassium batteries, and they delivered specific capacities ranging from 200 to almost 400 milliamp hours per rem, while other materials demonstrated good operational characteristics as cathode components, and we could reach energy densities up to 600 watt-hours per kilogram. And optimization of the potassium batteries using new polymeric electrode materials allowed us to achieve simultaneously high energy density, high specific power, and excellent operational stability for more than 10,000 cycles, which makes these devices a good alternative to supercapacitors and also promising technology for scalable stationary energy storage. I want to thank my colleagues who contributed to this study, funding agencies for financial support, and you for your kind attention.
Thank you. Thank you. Any questions from the audience? Yeah, okay. So there is what is the ion conductivity of this material used as a cathode?
Sorry, what do you mean ion conductive material?
I mean the conductivity of potassium
yeah, all these materials, since they operate as electrode components, they have decent electronic conductivity, which is enhanced sometimes by using additional carbon filler, and they also have decent ionic conductivity. Otherwise, they would not able to operate as electrode components of these batteries. I hope I answered your question. I'm not sure.
Yes. Okay, thank you, Pavel, and we'll move on to the next speaker. And if you guys have more questions to Pavel, and please email him. And our next speaker actually cannot make it, so I will just play the video he recorded. Can you guys see?
Vegas, and I'm going to be telling you about a new type of water electrolyzer that we have developed recently. First, I'd like to acknowledge my colleague shown down the bottom here, who did much of this work. Water electrolyzers are electrochemical devices that convert water into hydrogen gas in the form of bubbles at the cathode and oxygen gas in the form of bubbles at the anode. This shows what their architecture typically looks like. They're two electrodes. Than about 4% hydrogen. Hydrogen with about more than 4% oxygen is an explosive mixture, and so that's a safety issue that has to be addressed in electrolysis. Now, of course, bubbles, when they're formed on the electrodes, are potentially a major problem in water electrolysis because bubbles are non-conducting voids, and they typically sit on the electrodes for a while before they release. And while they're there, they block access of the water to the electrode surface. They create inhomogeneous current distributions and a lot of other negatives. But the main thing they do is create a high resistance. In other words, they mask the electrodes, and that masking effect creates high resistance. And so I guess we've been wondering for some time whether it is possible to produce bulk gases directly from the water without producing the gas bubbles. If you can get rid of these gas bubbles, then you can potentially improve the energy efficiency of water electrolyzers quite substantially. Well, there's a material that I should tell you about, which is called Gore-Tex. You've probably heard of Gore-Tex. Gore-Tex is sold in form of jackets and various other textile items. So if one has a look at the surface of Gore-Tex, this is showing a picture with a scanning electron microscope, then you'll see that it is pretty much a matte, very, very fine microfibrils of Teflon. That's what Gore-Tex comprises of. Teflon, of course, is strongly repelling of water. It repels water strongly. So Gore-Tex blocks liquid water from going through. But because of the pores, gases can get through. So a Gore-Tex jacket will, for example, allow water vapor from your body to pass through it. But if you get rain or snow on your jacket, it won't go through. Now, Gore-Tex has another important property, and that is that it displays what's called a gas capillary. So in this video, we're showing a sheet of Gore-Tex with water on this side and a gas chamber behind it. And we're placing air bubbles on the surface of the Gore-Tex. And those air bubbles are not going up as you would expect with buoyancy. They are being pulled through the Gore-Tex. That is because of this gas capillary effect. And this effect is really very similar to a capillary tube when it's placed on the surface of water, pulls water up. Vortex does the same thing with gas bubbles. And that's because Gore-Tex is so strongly hydrophobic, has a high surface energy. Gases love high surface energy materials, so they coalesce on the surface and effectively get pulled through Gore-Tex. Now, we wondered then if instead of putting gas bubbles on the surface of the Gore-Tex, we put a catalyst layer on the surface. And the catalyst produced gases. Would the gas go through the Gore-Tex? Well, in fact, it does, and I'll show you in a little while how it does that. So we prepared a series of electrodes where we took a Gore-Tex membrane, and this is just a cross-section of our electrodes. Took a Gore-Tex membrane and we coated it with quite a thick layer of catalyst, around 200 microns. And we incorporated inside that catalyst a nickel mesh, very, very fine nickel mesh as a current carrier. When we studied those electrodes, firstly, we found they were highly permeable to gases. And secondly, they were effectively leak-proof. There was almost no possibility of getting liquid water from this side to go through into the gas chamber. So there was no possibility of flooding. And that work is described in this paper now. We then took those electrodes and built sort of benchtop electrolyzers, small-scale benchtop electrolyzers. So each of those electrolyzers had two Gore-Tex-based electrodes that comprised the Gore-Tex membrane coated with a catalyst on each side. And then we would have a liquid electrolyte, which in this case was 6 molar KOH, so a standard alkaline electrolyzer. And behind each of the Gore-Texes, we had gas chambers. The anode gas chamber where oxygen came out, cathode gas chamber where hydrogen came out. We tried a number of different industrial catalysts and different gaps between the electrodes and different temperatures. So I'll show you here a video just comparing at 100 milliamps square centimeter, a bare nickel mesh making oxygen, and you can see there are lots of bubbles being produced there, with one of our electrodes, Gore-Tex electrode, that's shown over there, also at 100 milliamps square centimeter, there are no bubbles visible there. Right, so it really does get rid of bubbles. Of course, these are only bubbles visible to the naked eye. There may be smaller bubbles there that we can't see, but nevertheless, there are no obvious bubbles. Now, why are no visible bubbles produced? Well, we think there are 3 reasons. The first reason is that you're actually producing your gas very close to a liquid gas interface. But inside the Gore-Tex, there's gas. Outside the Gore-Tex, there's liquid, and the liquid permeates into the catalyst layer. So in the catalyst layer, you're producing your gas very close to that interface. And it's just simpler, easier for the gas to dissolve in the liquid and migrate across the interface than to form bubbles. That's the one reason. The second reason, as I mentioned earlier, is that PTFE has high surface energy, and so gases selectively will coalesce on that, so on the PTFE surfaces. And we know that they can move along those surfaces into the Gore-Tex. And the third reason is we think that gas capillary action that I mentioned, and we actually measured the capillary pressure of our Gore-Tex electrodes using the Young-Laplace equation. That came out at 6.3 bars. So it's actually a very high capillary driving force for that gas to be pulled in through the Gore-Tex. Now, the negative sign here only indicates the direction. Positive sign is what you would get with water going up a capillary tube, so hydrophilic interaction. In the case of a hydrophobic interaction, where it's gas going into the Gore-Tex, it's just in the opposite direction, so it's a negative sign. Now, to find out whether there was an effect on the energy efficiency of the system, we looked at the VI curves of those electrolyzers. And this is typically what we found. As you increase the temperature, there was a pretty dramatic decrease in the onset potential. went from about 1.48 volts at 40 degrees Celsius down to about 1.28 volts at 80 degrees Celsius. Now, to calculate the onset potential, what you do is you draw a straight line through the ohmic region of the curve, and where that straight line crosses zero current, that is your onset potential. Now, this is very different to normal commercial electrolyzers. They show almost no change in onset potential with increasing temperature. This system displays a dramatic change. And the importance of that is that, you know, every electrolyzer has a different impedance, a different resistance between the electrodes, and that's very much dependent on the cell architecture. So it's very difficult to actually compare different electrolyzers, but you can compare them in one way, that is at zero current. What is the voltage at zero current? In other words, the onset potential. Because at zero current, there's effectively no impedance, right? So the onset potential is effectively telling you about the intrinsic efficiency of the electrolyzer. And this particular onset potential is by far the lowest ever measured for an electrolyzer at 80 degrees. So it's telling you that this is intrinsically a very, very efficient electrolyzer, and that's because there are no bubbles. So just to give you a comparison, what I've drawn here is a whole series of BI curves for other electrolyzers, some commercial, some academic, at 80 degrees, and you can see that they all have onset potentials of above 1.45 volts. So 1.28 volts is really remarkably low. And we actually repeated this. We had this tested independently by an outside lab, and they also observed, they prepared the electrodes using our recipes. They also observed dramatically low onset potentials, which are indicative of high intrinsic efficiency when the effective impedance is stripped. Now, the reason for this very low onset potentials is because in the absence of bubbles, the overpotential declines dramatically as temperature increases, and it's particularly dramatic on the oxygen side. So at 10 milliamps, 80 degrees Celsius, we found the overpotential declined from around 270 millivolts without Gore-Tex, so with bubbles, to about 110 millivolts with Gore-Tex and without bubbles. So dramatic decline, right? And that's because there is no bubble curtain, and so there is no resistance associated with it. Well, we also then tried to build some actually electrolyzer cell stacks. So commercial electrolyzers have many cells that they stack, what are called cell stacks, in a filter press arrangement. And so we made these cell stacks. This is plastic, thermoplastic thin cells, to which we welded two Gore-Tex electrodes and created a gas pocket in between. And we could then stack these in a stack. And what we found was that there was one problem with using Gore-Tex in this way, and that was that Gore-Tex was non-conducting. And so to make your electrical connections between the cells, we actually had to have a bus bar on the edges and weld the Gore-Tex electrodes to those bus bars. And the current then had to flow through the nickel mesh that I mentioned earlier to the bus bar before it went to the next electrode. And so there was this long pathway through the nickel mesh, which created a small amount of resistance. It wasn't a significant resistance, but when you stack all these cells up, then those resistances stack up additively. And so we couldn't put more than about 50 cells together without those resistances adding up, becoming high enough that they counteract the benefits of operating bubble-free. So since that time, which we realized back in about 2017, 18, we've been trying to come up with ways to get around this problem. And that really meant avoiding Gore-Tex, trying to get a bubble-free system without Gore-Tex. We have now achieved that. We have a new system which doesn't use Gore-Tex. And our best data to date without the Gore-Tex is shown here in comparison with the best commercial alkaline electrolyzer, we think this is from Asahi Kasei, this is where we got the data from. And so that electrolyzer operates, we think, at about 0.5 amp per square centimeter. And you can see that at that current density, they need about 1.77 volts, which is about 83% energy efficiency, according to the higher heating value of hydrogen HHV. Our system got the same current density at about 1.52 volts, which equates to 97% energy efficiency. That's a 50% improvement. Even at higher current density, 700 milliamps, they would need 1.84 volts, 80%. We need 1.55 volts, 95% energy efficiency. And even at 100% energy efficiency, which is 1.47 volts at 80 degrees Celsius, we actually get a pretty handy current, 300 milliamps per square centimeter. That's certainly enough to build a commercializable water electrolyzer. And so in this region here, we actually have a cell that operates at 95 to 100% energy efficiency. Now, we haven't published this work yet, but we will be publishing it shortly. So we're very excited. And the last slide I'll just show you is our alkaline system actually beats even the best commercial PEM electrolyzer. So I think there is a lot of potential in this bubble-free concept as a means of getting really energy efficient electrolyzers. Thank you for your attention, and I'll be happy to answer any questions that arise.
So thank you. So we are going to move on to the next speaker, and I would strongly encourage you to email the speaker if you have any questions. How do I stop sharing? Okay, so our next speaker is Taras Marinauskas, and from Kaunas University of Technology. Are you there? Okay. So things I was not informed ahead of time, and the speaker is not here, so let's move on to our next speaker. Jinhua Guo. Got confused now. Let me see. Apparently, he is not here as well. Interesting. Can you guys hear me? I feel like I'm the only one in the room.
Yeah, we can hear you.
Okay, thanks. So we will just go down this list. Then whoever is here, we'll let them talk. Next is on the. Yeah, this is very challenging to me. It's like I've never been a session chair, which you started 10 minutes late and have multiple speakers not in the room. So our next on the list. Yes.
I think I'm the next presenter.
Oh, okay, that's great. Yeah, please go ahead. So our next speaker is Linda Centers from Gallenberg Tech Constituents. Can you share your slides, please?
Oh, yeah. I'll share my pre-recorded video.
Oh, okay. Yeah, please go ahead. Could you start the video?
Could you hear the video?
Yes.
The sound of the video?
We can. Oh, I don't hear it.
No?
No, I can see it, but I don't hear it.
Oh, okay. Could you share it, please?
Oh, you mean share your video?
Yes.
I have to find it. So because the previous speaker notified me, actually send his video to me, so I could share it right away. Let me find yours. Wow, this is very challenging. Your side, there is no audio. Can you try again on your?
Yes, I will try again.
I'm sorry to speak out here. When you share your screen, you have to choose the option of the share sound. If you don't click that option by default is off. If you don't click that, there will be no sound. Yeah. So you should stop your sharing and reshare and make sure that option is on.
Okay.
I mean, you cannot access that option. You have to stop sharing and then reshare. When you reshare that option,
I found the first. So please stop sharing right now.
Yeah.
Thanks, Chair. This presentation will introduce a new 2D macroscopic material and its application to energy harvesting. The material is exfoliated and reassembled graphite, nicknamed ERG. It has previously allowed us to make flexible, inexpensive, and corrosion-resistant electrodes for various purposes. This presentation will show their application for harvesting energy from the atmospheric moisture that we call hydroelectricity. Discovering ERG resulted from exploring the hypothesis presented by Bjorn Lindemann earlier in the century on the amphiphilic character of cellulose. Cellulose is known as a hydrophilic solid, but it's also oleophilic. Its amphiphilic character derives from the structure of cellulose chains, with flat hydrophobic surfaces surrounded by hydrophilic edges. This singular structure allows cellulose chains to adsorb on graphite flat surfaces, dismantling the crystals. Thus, cellulose is an effective exfoliant and water dispersant for graphite, producing water dispersions that dry on many surfaces, forming highly conductive films. ERG film resistivity is higher than graphite and much higher than graphene, but the cohesive films with thousands of lamellae show low surface resistance. ERG dispersions are prepared by adding graphite powder to alkaline aqueous cellulose solutions and mixing, taking care to separate lamellae but not breaking them. The dispersions easily cut different surfaces using various painting and coating techniques. The equipment used is widespread in painting industry, and the fabrication process requires mild conditions only. Thus, process scaling up should not present significant difficulties. Our current capacity is 100 kilogram dispersion per day. The result of painting it on wood, paper, brick, and many other materials is an adherent electrically conductive surface. ERD coatings are multifunctional. They are electrically conductive and are suitable for making flexible circuitry on various surfaces. They have already been used to make electrodes for electrochemistry, electroanalysis, and environmental control. ERD electrodes are inexpensive and resistant to corrosion, which makes them well suited for hydroelectricity. Completely different applications are highly efficient heaters and flame-resistant coatings for wood. Hydroelectricity is energy harvesting from atmospheric moisture. It was first demonstrated in 2010 when we showed that metals acquire charge under high humidity. This finding opposed prevailing paradigm, but charge exchange with the atmosphere also explained many other phenomena. We explained it by considering the partition of adsorbed or intercalated water ions from atmospheric water vapor, analogous to well-known electrification of solid and liquid interfaces. Energy harvesting from atmosphere's moisture has been verified by many authors in different countries using different materials, arrangements, and following our, but also other explanations. A few examples are in this slide showing results obtained using various types of graphene protein nanowires and metals. Assessment of the performance of a hydroelectric cell starts by allowing it to charge continuously for a given time. Connecting the cell to a capacitor using the switches seen in the schematic circuit allows charge transfer. Switching is controlled by a computer using a program that allows us to change the duration of each step. Recording the voltage between cell terminals and across the capacitor terminals as a function of time allows us to calculate the harvested and delivered energy and power. Harvested energy increases when the electrodes are wetted by just touching the water. However, soaking the electrodes decreases the amount of harvested energy. This slide shows the performance of a cell within a plastic box placed outdoors for a few days while the cell and the capacitor voltages were measured continuously. Cell and capacitor voltages increase during the day due to the higher temperature and thus to the higher partial water vapor pressure during the warmer hours. The energy transfer to a capacitor decreased during the cold, cooler nights, showing that the process responsible for keeping the electric current is strongly temperature dependent, endothermic. Hydroelectric cells are bipolar, and their connection in series or parallel arrangements is easy. A 4-cell battery made from improved electrode materials delivers 50 milliwatt continuously to a resistive load. These cells were also connected to a switching circuit, supplying energy to 12 LEDs during 4 minutes and resting for 1.5 minutes for recharge, cyclically for many hours, many times. This table allows a comparison between different devices harvesting energy from atmospheric moisture. The devices just presented show impressive performances, mainly due to the facility to build sizable cells thanks to the availability of the electrode materials. Using the water splitting reaction as an energy source may look surprising, since this is well known as a non-spontaneous reaction under standard conditions. However, in the present case, this reaction occurs in an open and non-electroneutral system, when water may enter freely, while the resulting gases can also leave freely. The thermodynamic reaction quotient, QR, is then much lower than the equilibrium constant continuously driving the reaction towards the products. Indeed, hydroelectric cells stop working if they are within closed packages. Concluding, exfoliated and reassembled graphite makes suitable electrodes for hydroelectric cells that allow their scaling, achieving unprecedented power and voltage outputs. Materials cost is low, allowing us to foresee the practical use of hydroelectricity, delivering power to IoT and other devices in remote environments. I thank the Brazilian funding agencies, CAPES, CNPq, FAPESP, and our organizations on behalf of all authors. I also thank you for your kind attention.
Thank you, Leandra. And because of the time limitation, so if the audience has any questions, please email her or put it in chat because thanks she is here. We will move on to the next speaker, Tadas Malinauskas. I guess this person is not here. And I will just, I actually, in the meanwhile, I download all the videos. So I will just play here. And if you guys have any questions, please email to the speaker. And for those speakers who are here, will be giving the talk later. I will give you the, I would more prefer you present instead of me playing this. So let me know anytime.
Hello, my name is Tadas Malinauskas. I am from Kaunas University of Technology, Lithuania. And today I would like to share with you our research on whole transporting self-assembly monolayers as an effective approach for perovskite solar cells. So this journey has started more than 140 years ago when Alexander Stoletov constructed first photovoltaic device. And for some time, this technology was more of a curiosity without any practical application. And the earliest practical application was in space technology, when Vanguard 1 was the first satellite to have solar electric power. As you can see from this chart, so over the years, photovoltaic technology has developed quite nicely, and all sorts of different approaches and technologies and ideas were developed and affected. And the efficiency of devices was climbing steadily over the time. And nowadays, the market is dominated by silicon solar cell technology, but I would like to speak to you about some other emerging PVs. In this case, in particular, perovskite solar cells. And over the last 10 or so years, efficiency of these perovskite solar cell devices has increased quite noticeably, up to more than 25%. And the tandems, silicon perovskite tandems, have reached almost 30% efficiency. Overall, the structure of a perovskite solar cell, general structure of a perovskite solar cell is depicted in this slide. So you have two electrodes, you have charge transporting materials, and the light absorbing perovskite in the middle. And you can have either regular structure, like here, where electron transporting material is at the bottom and hole transporting at the top, or inverted, where hole transporting material is at the bottom and electron transporting material is at the top. We, as a research group, focus our attention mostly on hole transporting materials, and they have a whole list of requirements. Among them, suitable energy levels, sufficient hole mobility and conductivity, also thermal and photochemical stability, and of course, another thing is reasonable cost, as if these materials would be extremely expensive, they would make little sense in practical applications. And in some cases, depending on the structure of your devices, good solubility is also required. So currently, most popular hole transporting materials, such as, let's say, gold standard, is spironolactone, and depending on the type of a device and person who makes it, efficiency ranges from 15 to 25%. Here in this slide, I have highlighted the most commonly used hole transporting materials. And as you can see, all of them are quite expensive, ranging from 250 euros per gram all the way up to 2,000 euros per gram. And just to compare them to gold, so gold costs around 40 euros per gram. So why they are so expensive? So one of the reasons why is really complicated and multi-step synthesis. For example, spironolactone, you need 5 steps to make this molecule. And also you need to use quite expensive purification procedures for intermediate materials and for the final one. The other issue with a lot of hole transporting materials is that they have low conductivity, which is not sufficient for good performance in perovskite solar cells. So you need to add additives, all sorts of dopants, which partially oxidize our HTM, and you have 2 orders of magnitude increase in conductivity. But this approach has its own drawbacks, and they are mostly reflected in reduced stability of the overall devices. So what can be done about it? So we propose a self-assembly monolayer approach for the hole transporting materials, where you have your molecule constructed out of 3 parts, so anchoring group, then an aliphatic spacer, and finally a functional group that is actually performing the function. So we took a molecule that was already performing quite well in perovskite solar cells and modified it. So we took half of it, added anchoring phosphonic acid anchoring group, which is among the most universal and strongest binding anchoring groups out there. And we ended up with first generation self-assembly hole transporting materials capable of forming self-assembling monolayers, which have anchoring fragment and also functional fragment. The application of these materials on top of metal oxides, conductive metal oxides, is really straightforward. You take your substrate and you dip it into this diluted solution of our HTM, and then you take it out, anneal it for 1 hour, and finally you rinse it and you wash away excess of the material, leaving just a thin monolayer on top of the substrate. Alternatively, you can use spin coating or spray to have the same result. Again, you use quite a dilute solution of sand material, and afterwards, after you spray it or spin coat it, you anneal it, and again, as before, so you rinse to wash away excess of the material. So we have tested this first generation SAM molecules in perovskite solar cells in cooperation with Helmholtz Center for Berlin researchers. And the devices show the efficiencies of around roughly 18%. It was a good result, but we thought that perhaps we can make it better. And we thought, what can we do about it? And we chose approach less is more. And in this case, we got rid of these diphenylamide groups. And we ended up with second generation SAM molecules. So if you compare devices constructed using standard reference material PTAA with the first generation SAMs, so you see that first generation SAM molecule showed worse performance. It was comparable, but still worse than the reference material. However, second generation SAMs already showed noticeable improvement in device efficiency compared to the reference material PTAA. We were also curious to find out, does this approach, the SAM approach, work just with this particular perovskite composition, or is it more universal? So we also tested the SAMs in with different compositions of the perovskite, also with vacuum deposited perovskites, and I'm happy to say that in both of these cases we have observed really good results, and so this is not just one trick pony approach. We also looked at the effects of spacer length. So does different lengths of the spacer influence the performance of the devices? And here you can see that as we increase the length of the spacer from 2 to 4 to 8 carbons, so initially there is very little difference in performance or fill factor, but as the chains get longer, so yes, fill factor and performance drops quite significantly. Looking at this, due to the nature of this technology, we figured out that it should work quite well in tandem approach, especially when you have textured or rough surfaces. So for test this approach in tandems, we have chosen CIGS solar cells, which are known for quite a rough surface, and the perovskite solar cells were constructed on top of them. So these tandems demonstrated efficiency of around 24%. The next logical step was, of course, to move to silicon perovskite tandems. And again, in this sort of setup, perovskite self-assembly monolayers demonstrated really good performance, and the overall devices showed more than 29% efficiency. We also done initial testing of initial stability testing. And if you look at the long-term maximum power point track, so the red line, so over more than 300 hours, the performance loss was less than 5%. And we also did a little bit of thermal testing, as we increased the temperature from 25 degrees to 85 and went back to 25. And we didn't observe any significant loss in performance of the devices. Just as a curiosity or as a side note, to show you that this approach is not just for perovskite solar cells, but could be tested in other solar cells as well. So I show you our work with researchers from KAUST, where SAMs were applied in organic solar cells, in particular this one. And again, in this case, we also observed noticeable increase in performance of the devices, and overall efficiency of around 18.4% was achieved, which is a quite good result for this type of technology. So overall, I would like to, I hope I showed you that this SAM approach works quite well in solar cells. And till the end of last year, we held 2 record performance efficiency records both in silicon perovskite and CIGS perovskite tandem devices. And these materials have been commercialized and are available from TCI and Dynamo. And if you want to test your devices, ideas that you have, so you can obtain them commercially. So just to summarize, we proposed an alternative to regular hole transporting materials. These hole transporting materials capable of forming self-assembly monolayers. And these SAMs have a whole list of very nice advantages, such as low material consumption. So you need really low concentrations of these molecules to make these monolayers. And this is dopant-free technique, which is also nice. And there is a negligible absorption, light absorption, which is quite logical if you think that you just have a very thin monolayer on top of your substrate. There's also a possibility of molecular design, so we can modify the molecules and make them more better suitable for different technologies and different approaches. These monolayers can be deposited via dipping or spin coating or spraying, and they're also suitable for tandems or textured or rough surfaces. And finally, I would like to thank the people who made this research, this presentation possible, and also our funding, and you for your attention.
Okay, so thanks. And again, please email the speaker if you have any questions about the presentation. And our next speaker is Jinghua Guo from Lawrence Berkeley National Lab. And I'm happy to see him in this room. So thank you. And please go ahead, start your presentation.
Okay. Thanks for the invitation. You see my slide?
Yes.
Okay, great. So my name is Jinghua Guo. I'm a senior scientist at Advanced Light Source in LBNL. So I like to present to you a tool, operando soft X-ray spectroscopy, and we use that to study interfaces in energy materials, especially under chemical transformation. The number of areas which will relate to the importance of interface reaction, for instance, especially for energy research area like photosynthesis, you spit water, produce hydrogen, or you're doing catalysis to make valuable chemicals. And also important battery application like a lithium-ion battery is very powerful these days in every areas, and the fuel cells as well. So all these energy devices or chemical reactions actually involving interfaces, and that also in many cases you have to look at the solid gas and solid liquid interface, and that makes important where you can look at the system in situ in operando condition. So the tools we have like to show you today is a soft X-ray spectroscopy that actually involving X-ray absorption, X-ray emission, and REX, and all these experiments are typically performed at a synchrotron facility. So at the beamline, and if you look at the cartoon now, you can actually see, you can choose the excitation energy. You can excite the carbon-1s electron to a conduction band. And then you leave a core vacancy behind, then the valence electron can come down to fill that core vacancy, and the energy difference can convert to another X-ray photons. So in all this process, you can include X-ray absorption, X-ray emission spectra, which is shown in the middle, the bracket here. And this is a comparison, a simple system, only formed by carbon atoms. So depending on the atomic chemical bonding structure, and that informs a graphite, you have a layer structure. and a diamond, which you have pretty much a 3D network of pi bondings, sigma bondings. So in the X absorption, you see the curve at the right. In the graphite case, that you will see the pi star, sigma star, because you have both type of chemical bonding in the system, while diamond only shows the sigma star. And that's actually, it tells you the X absorption can give you information about the chemical bonding and can separate them and can use them not only for these two cases, but there are many other carbon systems you can work with, so polymers or graphene and many other materials. And X-ray emission, to see the right, you're actually seeing the spectral shape change as well. So the valence band system are different too. And so the basic feature for that is that you get element selective, because if you look here, carbon, it's around 280, 85 EV in the neighborhood. But if you look at other elements, so you look at the different energy window, like oxygen will be at 530 EV. And also we show here, it really gives you the chemical sensitivity of the method. And then if you look at another element, for instance, the manganese, one of these 3D transition metal elements, and you can see if manganese at a different oxidation state, then they will have actually some spectra in the shape. For instance, the 2+ give you a very fine shape at the lower photon energy. And then we see you increase the manganese oxidation state, then the spectral shape towards the high photon energy and getting broader. So you can actually use that as your fingerprinting, and then you use that to study the chemicals and also chemicals and different chemical reactions. And here is an example in a little bit complex system, a lithium-ion battery, and that has two metal centers like a manganese and iron. So you can discharge cycle the electron material, and then harvest the sample and trying to determine which metal would be potentially the redox active side. And if you look at that with iron, LH spectra, this resonance edge is around 710 EV. And you see that the spectral shape, you start with estimate this material, the red curve on top, and that's indicate iron is at the 3+ oxidation state. And then if you're doing discharge, you see the spectral change, reduce iron to 2+. And when you charge the system, and the blue curve will get back to the same as the red one, you get the iron 3+ again. So that's a oxidation change in iron side. Well, in manganese, you see the spectral shape remains the same for estimate material, the red curve, or discharge or charge state going through red, green, and blue curve. So, and that comparison will show you that iron will be the redox active side in this system. And then the experiment set up, when you do X-ray absorption, you can make it the method to be sensitive to different surface or interface for your sample. For instance, if you use a very grazing incidence, then you can make this method being very sensitive to top layer material property, or the photons can actually penetrate through very much deeper, say 100 or more than 100 nanometers. Then here you can actually either you detect the TEY, which is total electron yield. Then because of the escaping depth of the electrons are very short, so you make the method being surface sensitive again. You can probe on the top surface a few nanometers. But then if you detect the fluorescence come out from the sample, then the method you can be a box sensitive. So you can either use that to study barrier layers or interface structure. So if you use the interface structure, then you can actually think about, say, in a battery application, you have the liquid electrolyte. Then if you want to get information about the interface, like a solid liquid interface. So in the system, we probably adding an X-ray transmission window and kind of to keep the liquid within a reaction cell, because soft X-ray has to be performed in an ultra high vacuum condition. But this way you can actually build a cell to do that, and then X-ray come in, and then either you can, as we say, you can detect the TEY, you can make the mass being the interface sensitive, or you follow the fluorescence, then you can actually look at the electrolyte from bark and then deposit getting to the interface, or you can further actually follow up the ion diffusion in the electromaterials. So that's very powerful when you study electrochemical reactions or battery reactions. So you can actually apply the bias over to mimic battery performance. And also you can study catalysis while you're involved in a solid state gas environment. So the gas molecules could be absorbed, dissociate on the catalytic surface or interface, or interact with other molecules or atoms around to form a new chemical species. So in this case, again, I didn't plot here, we can actually adding X-ray transmission windows, so we can preserve the gases in the cell, and then same thing, we can actually start to record the X-ray absorption from the interface, or using the fluorescence yield detection to get a bulk sensitivity. So the way we do it, typically we use silicon nitride window. As you can see here, it's a very conventional way of making silicon nitride membrane windows, and that allow you to preserve the liquid or gas in the cell, but also the membrane allow soft X-ray transmission being in and out. So here it shows the transmission of soft X-rays through the 100 nanometer, say, silicon nitride window, the red curve. You can see if you study carbon species, you get almost a little bit close to 50% transmission. And then as you using higher photon energy, look at the oxygen K and LH, then you can see the transmission actually getting higher. And of course, you have trouble to study nitrogen, and at about 400, it's about 400 EV here, and the silicon, because it's silicon nitride containing elements. Then you can actually also using a carbon-based window, the black curve, that you lose carbon resonance KH, but then you can use this for other photon energy. So with combination of these two, you can actually build, say this is a liquid static liquid cell. You can have a gas flow cell, liquid flow cell, and this is just cartoon, but we actually build various different cells for various different experiments. And also in the liquid cell, you can add electro contact, make it working electro and counter electro, mimic electrochemical condition. Here is example, look at the water, liquid water interface with gold interface. So the left up corner, you see the first experiment showing the curve A is actually TFY, fluorescence detection, give you the bulk sensitivity. The information come from the bulk water. So you see that's a pre-etch feature coming up. And while at the same time, when you record the TEY, the second curve, that pre-etch feature disappear. That's an indication, and the molecular structure of water at the interface to gold surface, actually the change from the bark. And if you actually modify the gold surface, you use this organic molecule, and then you can actually see the circle C come up, the prefetch come up again. So in this case, you can actually see only in the metal surface, you see the different molecular structure of water. And also through the cell, you can actually apply a bias over, so that will produce electrochemical current. and that's actually a challenge when you're recording the TEY, the electron yield. So the way we overcome the challenge is that we using a piezo-controlled chopper to modulate incoming X-rays. So, and then you have locking amplifier to tune that frequency, and then you can actually decouple that photon current from the X-ray excited from the electrochemical current, which is DC. So this way you can actually, again, recording X-ray absorbed spectra. So in this case, while you apply the different potential over the cell, you can actually see this pre-edge feature. It shows up again when you switch the potential towards to negative potential side. And you can see you can actually tune the water molecule structure through this way. Another in situ operando case is you look at the hematite, which is this original orange in color marked 30 nanometer thin film, which is supposed to be used as for the electrochemical catalysis for water splitting. So we studied the interface, and in this case, it's a little bit complicated because condition because you need to use the sunlight to excite the catalyst material, and then you follow up with electron hole pairs, and then by tuning the potential over the cell, then you look at what's happening. So here is actually absorption measurement to the left. There are two columns. One is dark, which means there's no sunlight illumination. The right column is under illumination condition. So we have a solar simulate the sunlight, and then the sunlight come in, it produce electron hole pairs, and then you apply the bias, the electron will go through the same film to counter electrolyte, and then the whole state will actually diffuse to the interface, participate the reaction. So that's what we follow up with seeing. To the left side, it looks like in any condition, different potential, the spectra, which is two peaks remaining about the same. And this is a typical fingerprints of the T2G splitting come from the iron oxide material. And then oxygen from water will shows up after 535 EV, which is not come into play, but in this plot. But we focus on the pre-edge. So once at the under sunlight illumination, then you're actually seeing the change. The T2GEG still remain the same, but then you're seeing this little green absorption feature come up. And then it turns out this features actually has two clear sides. And that's depending on if it's oxygen related or it's hybridized between the iron 3D and oxygen 2D state. So if you follow the intensity of that at the different potential, you can see these two holes adds up intensity. The gray curve, the rising slope is actually follow up with the blue curve, which is a photon current. And that's actually also a shift, which is about half volt, 500 millivolt. That's actually equal to actually the over potential of the iron oxide in this case. So this method actually can really tell you the chemical reaction and in its action. So with that, so I just showed you some basic unique feature of the soft-phase spectroscopy for X-ray absorption exclamation, and most actually for in situ operando capability for X-ray absorption, and then a couple of examples for its application. But because of time, I'm not going to more, but if you're interested, you can always email me, get potential your experiments done at our facility. So with that, thank you for your attention.
Thank you very much, Jinghua. And because of the time limitation, we won't take questions here. If you have questions for Jinghua, please put it on the chat or email him, and we will move on to the next speaker. So our next speaker is Xihong Peng from Arizona State University. Actually, I don't see the speaker in the audience. If you are there, let us know. And also, there is no presentation uploaded. So I will go on the next one, Baron Bora from University of Electrical Communications in Japan. Is the person there? Okay. Not, I will share. Just let me see. How do I do this?
Hello, everyone. Hello, everyone. My name is Varun Vora, and I'm an associate professor at the University of Electrocommunications in Japan. But obviously, as you can see from my face, I'm not Japanese. I'm actually French. But anyways, I would like to thank the organizers for inviting me to give this talk today, despite the coronavirus situation. And today I will be talking about organic solar cells and sustainable methods to fabricate these organic solar cells. But before we start, we should talk about a global issue, the global energy issue, and the importance of solar energy. As you can see from the map here, solar radiation is present everywhere on the global scale. And in particular, it's very abundant in sub-Saharan countries, for example, or other low-income countries. So if we take the example of Ethiopia, which is located here, you can see that with the annual solar radiation, you could easily cover the energy demand per capita. Actually, you would need just a 1 square meter solar cell with a 5% power conversion efficiency to cover this energy demand. And this makes us wonder, why don't low-income countries harvest more solar energy to cover their energy demand? And there are a couple of reasons, but the most obvious one is that conventional solar photovoltaic technology is quite expensive. So the common solar panels that you can see everywhere on rooftops or anywhere around any city in the world are made with silicon technology. This means that you actually have to fabricate your panels through very costly using very costly materials, but also processing them at very high temperatures, so typically over 1,400 degrees. So it has a high cost and a high carbon footprint. And of course, you have to do additional advanced processes here. The other problem is that it's usually, these kind of solar cells are rejected by local communities because they disturb the natural sceneries. They're not really in harmony with local architectures. So in particular, for example, historical places, cultural places, they will disturb the view, basically. And the other thing is that they're heavy and not really easy to install. So in addition to the cost, there are other things that are hindering these kind of silicon-based photovoltaic technologies. And a lot of people end up being like this, that it's too costly and too ugly for them. So is there a technology that is more suitable for these low-income countries and in general for everyone? Yes, there is. And this is what we will be talking about today, the organic solar cells that are based mainly on conjugated polymers. So the active layer is, you're basically replacing silicon-based active layers with organic semiconductors. And one of the organic semiconductors conventionally is a conjugated polymer. So because of this, you enable low cost and low temperature processing because of the filmability of these polymers. You can use something like spin coating. So using spin coating, you can actually achieve record power conversion efficiencies around 18% now. So this used to be around 10% 5 years ago, 5-6 years ago. It's growing very quickly and actually scarily quickly. So we can expect these efficiencies to be similar to silicon-based photovoltaic technology within maybe a couple of years or 5 years. So the interesting part is that you can actually fabricate your devices using something like inkjet printing. So you can even think about fabricating your own solar cells at home. or through, for example, painting like you would paint your car, or actually printing like your journals, or anything that is high productivity roll-through-roll process, basically. The other thing is that because of their semi-transparent nature and lightweight, they can actually be in harmony with cities and with nature. So for example, you can think about these kind of futuristic applications where you have a fully solar-powered sports car. So this is a concept car by Nissan, by the way. So it's using solar windshield. So everything here is a solar cell. You can think about solar trees that you can basically blend within nature or within any urban environment, and solar windows. This is a paper that we published a couple of years back, where you can see that you basically see the same thing as a normal window, slightly darker, but you can generate power from your window, basically. So how do these organic solar cells work? The working principle is actually quite straightforward. You need two materials in your active layer, one electron donor, which is usually the conjugated polymer, and an electron acceptor, which can be either a fluorine derivative or a non-fluorine derivative. What happens, so I'm giving the example actually of what happens when the electron donor absorbs light. So you have light absorption, which generates an exciton, so a Fresnel exciton, that will diffuse to a donor-acceptor interface. And at the donor-acceptor interface, because of the difference in LUMO of the two materials, the promoted electron will basically transfer to the LUMO of the acceptor. And that will be how you generate your electron on the acceptor and your hole on the donor. So that's what I represented here. With these colors here. So this is the electron, one additional charge, and this is the hole where you have one less electron, say. Then these charges have to be transported to their respective electrodes, and that's how you generate the photocurrent. Now, I won't go into details, but you have to keep in mind a couple of things, that the JSC, basically the short circuit current density, is related to the amount of interface that you have, donor-acceptor interface that you have in your device. But also the crystallinity of these materials will play an essential role in terms of charge collection. So crystallinity will increase the field factor of your devices. And of course, one of the major parameters that people look into is the power conversion efficiency. I was talking about this before. But anyways, these devices are great in principle, but they have one major sustainability issue, and I will talk about this now. So the problem comes from the fact that even though they can be solution processed, the solvent that is used for depositing these kind of active layers are usually very bad. So it's chlorobenzene or dichlorobenzene, which, as you may know, they're actually very toxic. So they result in air or water contamination or diseases, basically. And the other issue is that the conventional way that people deposit the active layer to obtain high quality and high efficiency devices is by spin coating. So what happens when you spin coat is that through centrifugal process, you basically elongate your solution, and you fabricate wet films, and then from there, within seconds, you can fabricate dry films. The issue is that when you do this, you actually eject 90% of your solution through this centrifugal process. And these 90% contain high cost materials, so relatively high cost materials, and also these toxic solvents. So we want to reduce these kind of wastes. And to do this, what we looked into is a technique called push coating. This was developed in 2012 for one of the most common conjugated polymer. Everyone might be familiar with this name, P3HT. The working principle of this technique is very straightforward as well. What you do is you use a silicon elastomer made with PDMS, so polydimethyl siloxane, that you placed on a very small amount of solution, so active layer solution or any other organic semiconductor solution, which is basically 20 times less than what you would use for spin coating. And when you put this elastomer here on top of this through basically capillary forces, you will elongate the solution between the substrate and the PDMS stamp. And then the solvent will diffuse inside PDMS, and you will be able to generate a very high quality film. Now, when you do this, because you fabricate your film just until the edge of the PDMS, so it's due to the capillary forces, it's a very sustainable fabrication method because you have no active material waste. The other thing is that the toxic solvent is temporarily trapped inside PDMS, so it can be very easily recycled. So it's good for nature, it's good for your health, and it's also good for your wallet. Now, what happens when we try to compare the performance of devices made by push coating with devices made by spin coating? The first actually trials were mostly for organic field effect transistors using P3HT, and what you can see is that compared to spin coating, when you look at push coated films, you can see a much higher crystalline order in push coated films compared to spin coated films. So in the case of P3HT, this led to very high hole mobility values of 0.47 centimeters square per volt seconds, which is one order of magnitude higher than what we get for spin coated films. We also more recently tried to make organic light emitting devices using, for example, F8BT or MEHPPB as emitting layer. And in these devices, we also saw that the efficiency, so the external quantum efficiency, is enhanced with respect to spin coating. So this is great for this single material layer, but in the case of organic solar cell active layer, you're actually blending two different materials, and the drying dynamics of spin coating and push coating are very different. So we were wondering if it's also possible to do the same thing with organic solar cell active layers. And we first checked this with the, the state-of-the-art materials for organic solar cells, P3HT and PC61BM. So these used to be very often employed until 2012. Now it's getting a bit more rare, but they're still considered the best materials to study the fundamentals of organic solar cells. In this case, we compared spin coating, where you need a post-annealing to increase the crystallinity of P3HT, with push coating, where no post-annealing is necessary. And as you can see here, so comparing spin coating and push coating using two different solvents, so chlorobenzene or dichlorobenzene, we get very similar power conversion efficiencies. And one thing that you can clearly see here is that the push coated films actually generate much higher fill factors compared to spin coated films, despite being annealed. So this is related again to higher crystallinity in your active layers, which basically promotes your charge transport and charge collection. And because of this, you can have very high charge collection efficiency. Now, we can also see a slight decrease in JSC, which is most probably due to larger phase separation, because you're giving more time to the films to form due to the slower drying dynamics, basically. And because of this, you might generate this kind of detrimental phase separation and slight decrease in JSC. Now, what we thought is, can we avoid this detrimental phase separation by using a more amorphous system? So we moved to another system composed of PCDTBT, which is an amorphous conjugated polymer, so a copolymer actually, and PC71BM, which is a fluorine derivative that absorbs visible light. And what we can see here is that despite being more amorphous, if you compare to annealed spin-coated films, you actually see the formation of aggregates in the films of PCDTBT, PC71BM. Here, I didn't write it, but the ratio is 4:1, 4 PC71BM to 1 PCDTBT. So most probably these aggregates that we see on the surface are PC71BM aggregates. Despite this, we still get similar power conversion efficiencies for spin-coated films, annealed spin-coated films, and push-coated films processed at room temperature. So now this is quite a nice result because it shows us that we can get similar or higher performance compared to spin-coated with push coating. But as I was talking about in my introduction, actually spin coating is not the only process that we can use to manufacture your solar cells, and most probably other processes will be used for when it comes to commercial fabrication. So we try to compare basically push coating with other probably commercial processes, like future commercial processes like blade coating, which is represented here, or spraying, which is represented here. So if you look at this this table here, you can first of all see that The only process that has similar power conversion efficiencies to spin-coated films is push-coated. And the second thing I want to draw your attention to is that in terms of volume of toxic solvent that you use, push-coated actually has the lowest volume of all of these processes. What comes next, second in line, is blade-coated. And actually in this case, even though in terms of volume of toxic solvent, it doesn't seem to be so bad. Blade-coated still uses twice as much as toxic solvent as push-coated films. And also in terms of power conversion efficiency, blade-coated films usually generate lower power conversion efficiencies compared to push-coated ones. So these are great results, and it works really well for conjugated polymers associated with fullerenes. But for those who are familiar with organic soil cells, they know that to get, for example, power conversion efficiencies over 10%, we have to move towards non-fullerene active layers. And we did some initial tests there with one of the new reference in the field of organic soil cells, so PBDBT ITIC active layers. Again, these molecules are represented here. These are very crystalline molecules, and usually one of the requirements to achieve high power conversion efficiencies over 8.5% is that you can actually crystallize both materials at the same time. And what we tried to do here is to compare the push-coated and spin-coated films fabricated from chlorobenzene with a solvent additive called diiodooctane. This is actually a solvent additive that promotes crystallinity. And what we saw here, and it's more obvious in the out-of-plane results, is that ITIC actually over-aggregates in the push-coated films, whereas in the spin-coated films, you can clearly see that PBDBT crystals are present, and also ITIC crystals are present. So this over-aggregation of ITIC here actually hinders the formation of crystalline domains of PBDBT. And because of
So everyone, I'm forwarding this video just because I think this video is super long, so it is not fair for the in-person presenters we actually cut off the presentation. So if you have more questions later on, always ask the speaker, and if you have any questions, because so our next speaker is Carolina Jokavs is the speaker here. Okay. So apparently not, I guess. So again, I will play the video.
Hello everyone, my name is Karolina Jurkiewicz. I'm from the University of Silesia in Poland, and it is a great pleasure to give this short presentation on this conference. Today I'm going to talk about developing of the structure of non-graphitizing carbons as alternative materials for anodes in lithium-ion batteries. So nowadays, the state-of-the-art materials for anodes in lithium-ion technology is natural and synthetic graphite due to its low working potential, quite high reversible capacity, and cycling stability. The artificial graphites are usually produced by graphitization of coques, which are called soft carbons. In contrast to soft carbons, non-graphitizing hard carbons exhibit wide plateau on the cycling profile, providing much higher capacity related generally with the micro and mesoporous structure. So the porosity and the small size of the graphite light domains provide fast lithium transport channels and reduce the solid electrolyte diffusion lag for lithium, and thus render the cycling rate. So the microstructure of hard carbons can also buffer well against the local volume change during lithium insertion and thus enhance the stability of the structure. However, simultaneously, the nanoporous structure and high fraction of edge sites cause the solid electrolyte interface formation, reducing the initial Coulombic efficiency and capacity with cycling. Moreover, it results at lower energy density than graphite. So the aim of my studies is to develop low-cost and easy in production materials based on hard carbons with improved capacity compared to graphite and better cycling performance compared to standard hard carbons. I focus on the synthesis of graphite materials capable of providing a compromise between high reversible capacity and low irreversible capacity loss. As you can see, these both properties are directly correlated with the specific surface area of graphite. So the idea is to produce materials based on hard carbon with reduced surface area and enhanced degree of graphitization. For this, I employ the process of catalytic graphitization in the assistance of the silicon-based catalyst. So this process can be carried out in two ways. First, the way is the addition of the silicon-based dopants to carbon precursor and heat treatment at standard graphitization furnace at 3000 Celsius degrees. The second way is that the pure hard carbon is heat treated in the standard graphitization furnace, but in the presence of the silicon vapor. And the resulting materials have slightly different properties, but they both resemble the atomic scale structure of graphite produced from soft carbons. So let's verify it. So here you can see the differences in the morphology of soft and hard carbons graphitized in the presence of the silicon vapor. So you can see that coke's form irregular lamellar-like particles, while non-graphitizing carbons from sucrose and purpuryl alcohol polymer, they form wires and various polyhedral crystals. So now let's have a look on the atomic scale structure of these materials. Here you can see the comparison of diffraction patterns of pure soft and hard carbons graphitized at 3000 Celsius degrees with their counterparts graphitized with the addition of silicon. In case of coke, you can see that there are almost no difference between both materials, catalytically graphitized or normally graphitized. They result in almost the same structural parameters. While in case of hard carbons, the presence of silicon dopant induces spectacular transformation of their atomic scale structure. That is manifested as the appearance of graphitic diffraction peaks, and also the drop of interlayer distance and increase of the size of the crystallites. You can see that they are comparable to the values obtained for graphite from coke. So globally, the graphite-like structure of catalytically graphitized high carbons is revealed. Also, Raman spectroscopy as a complementary global structural probe demonstrates the transformation of the structure of hard carbon when they are catalytically graphitized. So you can see that the size of the crystallites in plane direction calculated based on the intensity ratio of the D to G peak is comparable for cokes and even slightly greater than for graphite from graphitizing coke. So this is because the measured intensity of the D peak is comparable for both soft and hard carbons catalytically graphitized. So in turn, the high-resolution transmission electron microscopy showed that locally the structure of catalytically graphitized hard carbons differs from the structure of these carbons graphitized in the pure form at the same conditions, as well from the structure of soft carbons. So you can see fragments with great graphitized domains. However, you can also see that the nanoporosity is partially preserved in the catalytically graphitized hard carbons. So this results in higher specific surface area of those material compared to the artificial graphite from coke. However, the surface area can be tuned by selecting the proper catalytic graphitization method and concentration of the catalyst. So here, for comparison, you can see the carbon from sucrose, but graphitized in the presence of the silicon vapor. In this case, the BET area is significantly reduced than in case of sucrose sample graphitized, but in the presence of the silicon dopant. So the reduction of the porosity and the surface area is also confirmed by high skeletal helium density of this material that is close to the theoretical density of the graphite crystal. In summary, the hard carbons derived from sucrose and polyfurfuryl alcohol polymer graphitized at 3000 Celsius degree in the presence of some specifically selected silicon-based dopants or silicon vapor, in contrast to pure precursors which do not graphitize at these conditions. And the obtained nanographites from hard carbons do not contain catalytic impurities. They are pure carbon materials, and they have global structure resembling the structure of artificial graphite synthesized from soft cokes. However, the porous structure of hard carbons may be partially preserved and is tuned by the catalytic graphitization method. So the developed materials combine the structural advantages of hard carbons with the benefits of graphites, and the next step is their electrochemical testing in lithium-ion batteries. Thank you for your attention, and I am waiting for your questions. Have a nice conference.
Thank you guys for listening. And so again, if you have any questions to the speaker, and please email her. And we will move on to our next speaker, Veronica. And I really appreciate, Veronica, you are staying here, and please share your presentation. And thanks for your patience.
Okay.
So Veronica is from IJC lab, and please start your presentation. Thank you.
So do you see my presentation? Is it okay?
Yes, we can see it, but yeah, not perfect.
Okay. Oh, sorry. Sorry. Thank you very much for your introduction, and thank you very much for the organizing committee to give me this opportunity to present our research work, ionic liquids for the new thermoelectrochemical cells, or just thermal cells. This work was done in collaboration between two research groups from the University of Paris-Saclay and from the French Alternative Energies and Atomic Energy Commission. So it is well known that the energy production and consumption are accompanied by the significant heat losses, and but this waste heat could be an important power sources. Our goal was to develop new thermal cells for the direct conversion of low-grade waste heat into electricity at small scales. For example, for banks or in conjunction with larger power sources like solar energy. So in a classical thermal cell, we have two electrodes and immersed in an electrolyte and containing a redox couple. A temperature gradient is applied across the cell, and the generated voltage between two electrodes is associated with the entropy of the redox reaction. The magnitude of this effect is described by the Seebeck coefficient. So the reference system for all thermal cells is an aqueous solution containing ferricyanide, and the system shows a high Seebeck coefficient of about minus 1.4 millivolts per Kelvin. So, but until recent advances in the field, the performance of thermal cell was enough low because of the physicochemical properties of water solutions. So the current research focuses on the development of new redox couples, showing the high Seebeck coefficients dissolved in non-toxic, non-volatile, and thermally stable electrolytes like ionic liquids, as well as on the nanostructuring of electrode materials to increase the performance of thermal cells. So our study concerns the application of 1-ethyl-3-methylimidazolium trifluoride ionic liquid. This ionic liquid shows a high ionic conductivity and low viscosity. And as all ionic liquids, which are highly structured environment, the use of this ionic liquid may increase the Seebeck coefficient via phenomena of solvation and reorganization. So the second important point in development of the thermal cells is to find an appropriate redox couple. We were drawn to the literature data on the europium redox properties in ionic liquids, and it has been reported that the apparent standard redox potential of the europium redox couple is strongly dependent on the temperature, and its variation may achieve about 10 millivolts per Kelvin, and this value is very high for the thermal cells. So our goal was to understand this very interesting phenomenon and to use it in thermal cells. So as trivalent europium salts, we have used commercial salts as well as for bromides. And the solution of europium-2 trifluorides we have obtained by electrolysis. Now, for this electrolysis, we have used 3 electrode cell, and the complete conversion of europium-3 to europium-2, that black line, the reduction process before electrolysis. So, so the complete reduction of europium-3 to europium-2 species was proved by cyclic voltammetry study before electrolysis, black line, and after electrolysis, red line. So this electrolysis was carried out in a glove box under an argon atmosphere because the formed europium-2 species could be easily oxidized by oxygen. So the electrolysis data was also confirmed by UV visible spectrophotometry. So in solution after electrolysis, we may observe two absorption bands corresponding to Europium-2 species. And we have tested also the stability of Europium-2 solutions, the long-term stability, in hydrated and anhydrous ionic liquids. And the solutions were very stable to the hydrolysis. So the measurements of the Zibig coefficients were done in the thermos cell, in a homemade thermos cell with a small volume, and we have used glassy carbon electrodes. In a typical experiment, the position of cell was vertical, and the upper electrode was heated and the bottom electrode was cooled, and the cell was placed in a Faraday cage to avoid any electrical noises. And we have measured the open circuit potential with a high input impedance electrometer, and during several days to check the stability of our system. So, and we have calculated the Zibig coefficient from this curve. So we have divided the open circuit potential by the temperature difference applied. It was about 10 degrees, the gradient of temperature in the typical experiment. So we have also done electrochemical characterization of Europium solutions to detect all undesired electrochemical reactions in system, as well as to study the kinetics of redox reaction, and as well as to obtain the data on the diffusion transport of Europium species in solution. And first of all, we have studied the anhydrous solutions of Europium in the absence and in the presence of bromides. And we have found that in the absence of bromides, at low temperatures, the redox process is irreversible. But if we will increase the temperature or we'll add bromides in the system, so the process is reversible and diffusion controlled. So, but the measured Zibig coefficients was very different for these two systems. Without bromides, we had about minus 1.5 millivolts per Kelvin. That is the same value as for reference system. But with the presence of bromides, the Zibig coefficient was very low, less than 100 microvolts per Kelvin. So the addition of bromides decrease drastically the Zibig coefficient. So, but we wanted to verify if the high Zibig effects reported in literature was related to the presence of water in solutions, because in literature, in bibliographic studies, they used the hydrated salts of Europium. So we have done cyclic voltammetry studies in hydrated ionic liquid at different water concentrations, and we have found that the reduction potential shifts to a cathodic direction with increase of water content, and we have also improvement of reversibility of redox process. So in all water-containing solutions, we had high Zibig coefficients overpassing 4 millivolts per Kelvin, which is related to the high reaction entropy for mixed Europium water triethylamide complexes. So, but it was very difficult situation with hydrated ionic liquids in the presence of bromides, because the Zibby coefficient depends on the mean cell temperature. And so at low temperatures, we had high Zibby coefficients, about -3.5 millivolts, and at high temperatures, we had low Zibby coefficients, about -0.5 millivolts per Kelvin. So we have done spectrophotometric studies, and we have found that at high temperatures, European bromide complexes are predominant. So we have a low Zibby coefficient, and at low temperatures, the European water complexes are predominant. So it's in good correlation with our early data. So, and the European competitive complexation has a strong influence on the Zibby coefficient and on the performance of the thermocells. So, in conclusion, so the record values of the Zibby coefficient were obtained for European solutions in hydrated ionic liquid, and European complexation has a strong influence on the measured Zibby coefficients. And I would like to thank all my collaborators, host institution, and funded organization for the support of this work. And thank you very much for your attention.
Thank you, Veronica. And any questions from audience? If not, thank you very much. Actually, it is nice to even like seeing a person virtually. Yeah. So if not, we are going to move on to the last speaker of the session. Thank you for staying with us. And the last speaker also is not here, and we'll play the video they have uploaded. Can you guys see the video? Oh, somehow I think it's...
Yeah, hello. Thank you for joining for my talk, touching the forming SEI layer on lithium-ion battery anodes. My name is Frank Renner. I come from Hasselt University in Belgium. My group is mainly using experimental approaches for studying energy materials, using spectroscopy, also electron microscopy, spectroscopy, also AFM methods. Today we want to introduce another method, which is called, so just to give a very short glimpse of what my group is doing. We're looking, for example, at bulk energy materials, bulk battery materials, here in a model study of lithiation gold.
I don't know what's that. This is
So just to give a very short glimpse of what my group is doing, we're looking, for example, at bulk energy materials, bulk battery materials, here in a model study of lithiation gold. Gold can be used in various aspects of battery research, for example. And it's forming a sequence of crystalline lithium phases during lithiation. Using synchrotron radiation and high energy X-ray diffraction, we can follow a whole sequence of mostly metastable phases, and that's the first aspect of battery materials electrochemistry at room temperature. That phases and the materials you're dealing with often in a metastable state, as there's no time and no temperature for finding the equilibrium structure. Means also that the information is not available in databases, etc. My group is also called corrosion, but we use micro-contact printing to study localized corrosion, control the attack sites, localized control corrosion, and we are involved also in atomography on energy materials, which turns out to be complex and challenging. So today I want to focus on lithium-ion battery and mainly solid electrolyte interface, the study and use of surface force apparatus, study the SEI. The battery has many interfaces, and the so-called solid electrolyte interface forms on the anode. It's the reactive side, lithium potential. The organic electrolyte is decomposed. You have a decomposition film formed, which controls actually to a large part the behavior of the battery. It has to be transparent to ions, but on the other side also shield the high electrode potential of the anode towards the electrolyte. It has to be a compact but thin microscopic film, and it's of course important to study the detailed composition and the details of the structure as it determines the behavior of the battery. One method to study it is spectroscopy to address the composition. Method, for example, used widely is hard X-ray photoelectron spectroscopy, where the emitted electrons during the process have enough energy to leave even a thick layer. The SEI film has thickness in the order of a few tens of nanometers. So using Huxbus, we have the opportunity to study the complete film with a single measurement. Nowadays, not only at synchrotron radiation sources, but also lab sources. Today, I want to focus more on information beyond the composition of the SEI film, and want first to introduce AFM measurements, where you can, of course, get the morphology of the film. Also use force spectroscopy. With force spectroscopy, you have to deal with the fact that the AFM tip is quite thin and penetrates naturally the polymeric thin film, making data interpretation very difficult, to say the least. This doesn't get much better if you use colloidal tips, which have a much larger tip radius. That's still the order of a micrometer or so. Still having difficulties with data interpretation. The way out is using surface force apparatus, because we're not dealing with a standard surface and a very sharp needle that is used for the measurement, but we actually have two opposing cylinders that are brought into close contact, and the contact area is now a few tens of micrometer, so much larger than in the AFM case, and it's well possible to average over a lot of this larger area, especially when you measure mechanical behavior and forces occurring during force distance measurements. So the SFA can be also used electrochemical setup. I'm happy enough to have a collaboration here, use of the SFA with a group of Marcus Valtina at the Technical University of Vienna, which I want to acknowledge here. In a simplistic way, the surface force apparatus setup looks like this. So we have this cross cylinder geometry with two cylinder-shaped parts, which are used in our study with different materials. So first data point here is first data I want to show here is actually about wetting. So we use the SFA in a non-electrochemical environment. So simply having two different materials which are brought in close contact, and we introduce for these experiments the electrolyte by a syringe going into the argon atmosphere and distributing a battery electrolyte, which is in our case EC-DEC mixture of 1:1 and lithium PF6 as a salt. So wetting the surrounding has quite different impact when you use different materials, and that's one of the interesting aspects of this study here. So bringing into close contact, the zero distance is defined by the closest contact you can bring by applying reasonable pressures in the order of 10 to 20 bars on the contact here, and that defines actually our mirror shift zero, as you can see in the left plot here. Once you penetrate or you surround the battery electrolyte around the contact point, we see first a quite interesting behavior, that all the materials behave the same by even allowing a closer contact than before. You look at the numbers, the mirror shift changes here by about 2 angstroms, 0.2 nanometer, which can be correlated very nicely to water molecules. So that's also somehow expected, that we have a monolayer of water, which is very difficult to repel by applying pressures in the SFA in the first place. But once you wet the surrounding of the contact point with battery electrolyte, the organic mixture is quite hygroscopic, attracting water. So that leads that this water film is actually removed from the contact over a few tens of micrometers, which is an interesting fact. Only for the graphene surface, which is in contact here with battery electrolyte, we see a pronounced wetting behavior in the following of the experiment. Visible here by this huge jump, this huge step up. Which finally ends at a gap of 1.2 nanometer, around 12 angstroms. Thick layer is formed once the surrounding here is wetted. So the battery electrolyte can really penetrate in the case graphene surface is available. So the carbon atoms of the graphene interface interact positively with the battery electrolyte, so that it's sucked in to the confined area here, really opening the gap. It's quite a nice finding here. Wetting of graphene films or of graphite surfaces has such an effect. On the right part here of the graph, you see the population graph, where you again see the formation of this film, which is around 1.2 nanometer. So the experiment can be further performed by opening the gap, so allowing not only the wetted layer of electrolyte to enter, but a larger volume of electrolyte. And in this case, here, the arrow marked with S, the opening is happening and then closing down again. During the experiment, we can then experience layer formation and mechanical behavior distinct depending on which material is used. And that's an interesting finding, that the formation, the films closely depends on the chosen material. So for example, the red point here is the gold thin film. The wetted film on the gold shows this relaxation, while this behavior is not observed on mica couple, telling you immediately that also the structure and mechanical behavior of the formed films are quite distinctive. Very nicely to be seen again with the graphene interface, or the mica graphene couple, where we have a final layer thickness after applying strong forces here in a stepwise manner, in the order of 3 nanometers. So that's thinner than in the case here of mica gold, but it's still more than a monolayer of electrolyte layering. So we are forming here indeed a rigid film which cannot be repelled, and we results looks like that. So you have to read the experiments that we approach from the right side here at large openings. So the mirror shift or gap opening, and we close down the gap, and we see here the increase in forces that we need to apply. That's actually the behavior of electrolyte layering, squeezing out layered liquid layers from confined areas. Can be understood by the DLVO theory approach. And once we apply now currents and we see the potential drops, it's actually a sign of the SEI formation and finally of the lithiation, start of the lithiation of the anode. And we see that during the formation of the SEI, the shape of the curve here in the measurement, that's the force distance curve, it's plotted here, changes considerably. We see that there's a kind of a knee here, where this pure electrolyte layering, or the linear behavior here, this logarithmic linear plot, deviates then to this curved shape of the measurement. This can be understood actually very nicely again with the theory for polymers and the behavior that is expected for polymer brushes as described in Duchenne theory. So having a more numeric analysis shows that the layer growth is quite homogeneous and mainly determined by part of the interface as is seen here. I want to shortly wrap up, just telling you that the SFI is a great device to measure mechanical behavior of SEI films, can be applied in situ. We've presented first data here, and the device promises to be further applied in battery research in the future. Thank you for your attention.
Thank you very much. And I would like to thank you all actually staying here and till this end. And also I really appreciate all the speakers, especially those who presented virtually. And so this concludes our session today. And again, I really appreciate you staying here with me till this end, and really wish you next time we will be able to see each other in person in conferences. We are experienced the challenges having virtual. And also another thing is really wish we all know like the difficulties actually being in virtual conferences, and hope everyone would get a vaccine. Actually, this is I think get a vaccine and the COVID can be over as soon as possible. So I again really appreciate your stay, and thank you very much. And with this, I would like to say, have a great, I saw a message, so I just want to check before I end the session. So yeah, thank you all, and have a great evening, morning, or afternoon. And thank you, and see you next time in person. Bye.
Bye.
should be fine.